Hey guys, tonight we drift backward through the hush that comes before everything else, before stars, before atoms, before any name you have for color or sound. You listen, and the silence is not empty at all. It's a pressure of possibility, a kettle about to sing, a curtain trembling before the orchestra begins. We'll stand very gently at the shore of the first moment, the one cosmologists trace not with photographs but with careful echoes, like hikers listening for the shape of a canyon by the way their voices come back. Fun fact, you probably wouldn't survive being shrunk down to atom size, but we'll try anyway, purely in your imagination, and with very comfortable pajamas. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And tell me where you are, and what time it is. Chiang Mai at 11 p.m. Nairobi at dusk, Montreal beneath a soft flurry, because tonight we're sharing one origin, many clocks. Now, dim the lights, and let's ease into tonight's journey together. You close your eyes and feel temperature as a color white so bright it turns blue, then violet, then something beyond names, because the earliest universe glows with a heat so fierce that matter and light are one braided storm. Physicists reconstruct this, not by peeking into the first instant, our laws blink there, but by reading its fossil light, the cosmic microwave background, an afterglow stretched by expansion into a cold whisper, arriving from every direction like fine static on an old radio. Planck collaboration, 2018. You imagine that static as snow on a midnight TV, tiny speckles of brightness, not random at all, but a map of the universe's childhood freckles. From those freckles, careful teams derive the age, the ingredient list, the curvature, the pace of expansion, like tasting a spoonful of soup and telling what went into the pot hours ago. Planck collaboration, 2018. Peebles, 2020. You float inside that soup in your mind, and it has the texture of fog that's also fire. Photons bump into charged particles constantly, like dancers who can't quite take a step without finding another hand. You drift among them and hear a ceaseless clinking ping, 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 as if a trillion tiny bells are struck at once and never finish ringing. In these conditions, the word solid hasn't been invented by nature, neither has atom. What you have is a plasma, a kind of primordial weather where the rules are simple but the consequences are grand. The universe expands and cools. That is the rule. In the first fractions of a second, the energy density is so high that space-time itself feels tight, like a drumhead, its vibrations poised to seed all later structure. You consider how expansion acts like the universe's breath, in, out. Except here, it is only out, a steady slackening of the drum as the pitch falls and the fog thins. But how do you know any of this? This you of the night, wrapped in a blanket, listening to an origin story. You know because measurements return again and again to the same melody. Satellites such as COBE, then WMAP, and most precisely Planck, have fingered the chords in that microwave afterglow and found them in tune with a universe that began hot and dense and has been cooling as it grows. Planck collaboration, 2018. The spectrum of that afterglow is almost a perfect black body. The most ideal thermal light nature can make so exact that deviations are parts per 100,000, a straightness of line that lets you exhale and trust the instrument. As you float, you also feel the scale. The afterglow's tiny temperature ripples, mere tens of microkelvin, are the small lilt in an otherwise even hum. Those ripples are the seeds from which galaxies and you, listening now, later arise. And yet, there is a horizon to knowledge, a shoreline where our theories break like waves. You approach the so-called Planck time, roughly 10, -43 seconds after the beginning, and your physics falters. Quantum mechanics wants to jitter. General relativity wants to curve. Together they speak over each other, and the sentence dissolves. You stand at that edge and feel the vertigo of not knowing. It isn't failure. It's a promise. The way a locked door promises a room. You imagine the lock's metal, cool, smooth, with tiny scratches from keys that don't yet exist. In that pause, you realize that science is not a finished cathedral but scaffolding around a rising tower. We climb not to admire what we've done but to see farther. Maybe the universe just loves to repeat patterns, edges that open into new interiors, questions that bloom into better questions. For now, you start one layer down from the unspeakable instant where our equations regain their voice. In this early stage, The universe is homogeneous to the eye, like milk with no swirls. The pressure and density are nearly uniform, a great fairness spread across all directions. That fairness is not a guess, but an inference. The afterglow's uniformity to 1 part in 100,000 says the universe took its initial steps with extraordinary balance. Planck collaboration, 2018. You imagine turning slowly in a meadow at dawn, the light evenly soft no matter where you face, and knowing, from that symmetry alone, that the sun must be high and filtered by fog. Something similar happens here. The evenness implies conditions. The freckles imply gentle departures from perfection. Together they write the prologue. As the universe expands, energy redshifts. The waves of light stretch like taffy. You picture a violin string being pulled longer and longer. The pitch drops until what was once blinding white becomes a radio murmur. That murmur is now about 2.7 Kelvin above absolute zero. A temperature you could almost feel as frost on a window. Invisible yet crisp, Planck collaboration, 2018. You press your palm to the imagined glass and feel the cold of everywhere. It's humbling. The cosmos does not care for our daily excitements, and yet it has arranged, without plan, for a background that can be measured by a tiny horn antenna on a New Jersey rooftop, or by telescopes that sail above Earth's weather. The simplicity of the story, hot, expanding, cooling, makes a shape in your mind, like a smooth arc drawn in one breath. You wonder what it means to say, first moment. Is it a limit, like the smallest slice your knife can cut from a loaf? Or is it a bound where time itself detours into a realm without before? You taste the idea and let it melt like chocolate. The cautious answer is that our best models describe everything after the first flicker of describability. That is enough to give reliable, testable predictions about light element abundances, the pattern of CMB ripples, the growth of structure. Peebles, 2020. The bolder answers will come later in our journey, where you'll meet inflation's gust and speculations about how the curtain first stirred. For now, stay with the hum, the expanding silence that carries a memory of heat. If you listen closely, the early universe is not only physics, it is rhythm. Expansion sets a beat, scattering sets a buzz. Gravity lays a baseline that will, much later, gather matter into the halos of galaxies. You hear those layers and recognize something. Complexity from simple steps. A choreography that doesn't need a choreographer. It comforts you like the predictable pulsing of your own heart as you lie in the dark. Maybe the grandest reassurance is that this is not myth pretending to be measurement. It is measurement that's become, over decades, a new kind of myth. True, self-correcting, and generous with wonder. Planck collaboration, 2018. Peebles, 2020. And you, quietly breathing, are one of the instruments reading the afterglow. Because your atoms were made possible by those first choices the universe made when it was still just light and potential. You let that thought settle like dust in a beam of morning sun. The first moment is not a point you can touch. It's a limit you can approach with better and better questions. The beauty is not at the unreachable edge, but in the luminous trail it leaves across the ages, a trail that telescopes and minds continue to follow. So you lie back, feel the cool of the microwave sky against your cheek, and accept the kindness of not needing to know everything to feel held by something vast. You hover at the foggy edge we reached a moment ago, where equations whisper and then go silent, and you ask the old, stubborn question. Was there truly a first point, a pinprick of everything, or is that just where our map ends and we've sketched a dragon? Classical general relativity, proud and precise, answers with a firm nod. If certain reasonable conditions hold gravity attractive, matter well-behaved, space-time not doing anything too exotic, then geodesics, the straightest possible paths through space-time, cannot be extended infinitely backward. They stop. A boundary appears. That is what the singularity theorems of Hawking and Penrose show. Not necessarily an exploding dot, but geodesic incompleteness. A cliff in the road that time-like or light-like travelers can't cross. Hawking and Penrose, 1970. You feel this as a physical sensation. You're walking a dim corridor that narrows into a bright, impassable seam, heat pressing against your face like a door you cannot open. The theorems are built from a few elegant ideas. One is the Ray-Choudhury equation, which tracks how a bundle of nearby paths in space-time converges or diverges under gravity's influence. If the energy content obeys certain energy conditions, the kinds that ordinary matter and radiation satisfy, and if trapped surfaces form, as they do inside black holes or in a uniformly contracting universe, then the paths are destined to focus and end. No need for equations tonight. It's enough to imagine a field of fireflies whose flight lines, drawn long exposure across the night, bend inward, inexorably, until all lines terminate at a single blaze. In that image, the blaze is not a location in space. It's the end of the story those paths can tell. But you feel a tug of doubt, gentle and honest. Reasonable conditions might not be reasonable at firestorm energies. As you drift closer to the first fraction of a second, quantum effects swell like a hidden choir, zero-point jitters, foam in space-time, new states of matter that don't play by classical rules. The singularity may be the universe's way of telling you that the classical sheet music ends and a different notation begins. Even inflation, the rapid swelling we will visit soon, can't save you from beginnings in every incarnation. A general result, known as the Borde-Guth-Vilenkin theorem, shows that any space-time that on average expands must be geodesically incomplete to the past. Borde, Guth, and Vilenkin, 2003. You hear that theorem as a soft verdict. Expansion is wonderful, but it does not erase the need to ask what came before the overture, so you hold both truths in your hands. Classical gravity points to a boundary. Quantum hints that the boundary may be a mirage born from using the wrong ruler. You test alternative stories. One is the no-boundary proposal, where the earliest universe doesn't begin with a sharp edge, but with a smooth rounding off of time, as if the line of history curves into a hemisphere and then blossoms into ordinary time, like a great circle unfurling into a meridian. Hartle and Hawking, 1983. You picture yourself sliding over a polished marble dome, no corner, no crack, then coasting onto a flat floor that we call time's first ticking. In that view, the universe doesn't pop from nothing. It transitions from a region where before simply isn't a meaningful direction, the way north of the North Pole isn't a place you can stand. Another path rewrites the crunch entirely. In loop quantum cosmology, the granular nature of space-time, quantized like a lattice of tiny loops, can act as a repulsive force at extreme densities, turning a would-be singularity into a bounce. A contracting phase rebounds into expansion, not because gravity changes its mind whimsically, but because the geometry itself acquires stiffness at the Planck scale, preventing infinite compression. Ashtekar, Pawlowski, and Singh, 2006. You feel the bounce as a trampoline beneath your feet, taut and springy. You fall toward the center and, instead of breaking through, you are pressed back up by the fabric's hidden weave. In this telling, the first moment is a turning point, not an origin. The smell is metallic and clean, like a new spring uncoiling. Some proposals keep the bounce but change the choreography. Ekpyrotic and cyclic models imagine a slow, smoothing contraction that crushes wrinkles before a transition to expansion, perhaps through a brain collision in a higher dimensional space or through a controlled, ultra-stiff energy component that calms chaos. Khoury et al., 2001, Ijas and Steinhardt, 2018. You picture two vast, dimly lit walls approaching in silence, the air between them thinning until, with a kiss of light, a new expansion begins. The sensory image is not violent but ceremonial, like book covers closing and a new chapter page opening itself. You ask, sensibly, if many pictures exist, how would you know which one the universe framed? You listen again for testable notes. The singularity theorems are robust within their assumptions. They mark a limit of classical reasoning. Hawking and Penrose, 1970. The BGV result is wide-reaching and warns that inflation alone doesn't solve beginning. Borde, Guth, and Vilenkin, 2003. No boundary proposals predict specific statistical weights for different kinds of early fluctuations and geometries, which in principle touch the pattern of ripples you'll meet in the microwave sky. Hartle and Hawking, 1983. Loop quantum cosmology suggests subtle imprints in the early power spectrum. Tiny changes in how ripples of different sizes grew, especially at the largest, faintest scales. Ashtekar, Pawlowski, and Singh, 2006. Ekpyrotic scenarios advertise distinctive non-Gaussian fingerprints in the sky's freckles, a skewness in the distribution of brightness that careful instruments might catch. Ijas and Steinhardt, 2018. Each is a lantern you can carry into data, looking for familiar shadows. Meanwhile, your senses keep you grounded. The air in this mental observatory is cool, the instruments hum, the afterglow light you met earlier brushes your skin like silk. You remember the comfort of uniformity and the freckles that broke it. Those freckles, born from quantum seeds and blown to cosmic scale, are the relics any beginning must respect. If the universe bounced, contracted, smoothed, or rounded its early time into a dome, the afterglow's pattern must not be scrambled beyond recognition. Our sky is a stern archivist. It lets speculation in only if the catalogue number matches. You return to definitions, because words matter here. A singularity in relativity is not a piece of stuff. It's a failure of the manifold, a place the coordinates refuse to cover, a boundary of predictability. You steady yourself with that clarity. You can accept that physics points to an edge, without pretending you can step onto it. Maybe the most honest sentence is, classical spacetime appears to have a past boundary under broad conditions. Understanding that boundary likely requires quantum gravity. Hawking and Penrose, 1970. Board, Guth, and Vilenkin, 2003. The thought lands like a pebble in water, ripples expand, but the center remains quiet. With that quiet, you consider meaning. A beginning evokes creation, a bounce evokes cycles, a no-boundary dome evokes wholeness without edges. Your feelings shift with each picture, like light-changing tone on a gallery wall, but the scientific rhythm stays steady. Propose, predict, compare, revise. You breathe with that rhythm. Perhaps the universe is less a sentence with a capital letter and more a melody that fades in from silence. Its first bars suggested rather than declared. Maybe the universe just loves to repeat patterns, boundaries softening into transitions, cliffs into curves whenever you learn to listen with a better instrument. Before you drift to the next gust of our story, you run your fingers along the edge again. It's warm now, not forbidding. You can almost make out the grain quantum texture, energy conditions loosening, new fields entering the score. From far ahead, you hear inflation's swift breath gathering, ready to stretch tiny creases into smoothness. But you keep this lesson in your pocket. Whatever the first moment is, it need not be a point. It can be a principle geodesics that cannot extend, rules that change their form, a seam where two fabrics meet. The awe is not in declaring which is right tonight, but in knowing we can ask the question with this much care, in the dark, and be answered by sky-wide evidence. You feel it before you name it, a wind with no air, a swelling that does not push from one place into another but stretches the places themselves. It rises like a held breath, becoming the whole room, and you ride it the way a leaf rides a river that is also the leaf. This is inflation. The universe's swift exhale, a brief spell when space expands almost exponentially, smoothing wrinkles, separating once neighboring regions faster than light can whisper between them, not by breaking the light speed limit, but by changing the length of the road. Guth, 1981. Linda, 1982. The sensation is strange and clean. Distant points slip from you, as if the floor beneath every step lengthens mid-stride. You glance back toward the cliff. We just visited the boundary, where classical ideas falter, and watch it recede into a soft blur. You listen for what problems this ancient wind solves, and they introduce themselves politely. First, the horizon problem. Our microwave sky is nearly the same temperature everywhere, even in opposite directions, despite those regions being too far apart, under ordinary expansion, to have ever talked and agreed on a temperature. Inflation lets them talk first before the stretch and then pulls them apart. Like friends who coordinated outfits before sitting on opposite sides of the theatre. Guth, 1981. Second, the flatness problem. Geometry today looks very close to spatially flat, meaning the cosmic energy density once had to be tuned precariously near a critical value. During inflation, any initial curvature is ironed away, as the rapid swelling drives the ratio toward flatness, the way zooming out on a slightly bent line makes it look straight. Guth, 1981. Third, The relic problem. Certain high-energy theories predict heavy, unwanted leftovers, magnetic monopoles, and other exotic debris that we do not find. Inflation dilutes such relics to irrelevance, scattering them into near nothing, like a drop of ink whisked into an ocean. You ask what builds this wind, and a single field answers the inflaton, an energy that fills space and, for a time, stays almost constant as it slowly rolls down a gentle potential. Its pressure is negative, its equation of state close to 1, so gravity does something counterintuitive. It repels instead of gathers, and the fabric of space accelerates outward. You imagine pushing a ball up a very shallow hill that is also the sky. The ball hardly moves, so its potential energy acts like a temporary cosmological constant. Linda, 1982. The math you don't need tonight reduces to a feeling: steadiness. For a few dozen e-folds multiplications by e of the scale factor, around 60 or so, the expansion is nearly self-similar, each second like the last in its roaring quiet. While the universe zooms, quantum jitters keep their mischief. The inflaton cannot be perfectly smooth. Uncertainty shakes it with tiny fluctuations. Inflation stretches those jitters, pulling them from subatomic to astronomical scales, and freezing them as faint over and under densities, seeds that will later welcome gravity's gathering hand. You hear them as the softest static beneath the main hum, a hiss that becomes freckles in the microwave afterglow and, much later, the scaffolding of galaxies. Guth, 1981. Linda, 1982. This is one of inflation's deepest gifts, a mechanism that turns quantum randomness into cosmic structure, predicting a nearly scale-invariant spectrum ripples of many sizes with similar power, tilting just a little from perfect flatness. You hold that in your palm like a pale oval stone, simple, textured, faithful to observation. The wind cannot last. A field that rolls must eventually find a steeper slope, then tumble. When it does, its stored energy reheats the universe, dumping into ordinary particles. Quarks, electrons, neutrinos, photons. You feel the warmth come back, not as a blazing match in darkness, but as a sunrise washing a plain, sudden, gentle, unstoppable. This reheating lights the hot Big Bang we more commonly picture, the plasma you floated through earlier. Inflation, then, is not something against the Big Bang, but a prelude that sets its stage and tunes its instruments, readying the orchestra for a theme you already recognize. You check the sky for signatures, because stories convince most when the sky nods. Inflation predicts those almost scale-invariant, nearly Gaussian, adiabatic perturbations. The cosmic microwave background answers with a pattern of acoustic peaks, the way sound waves once sloshed in the primordial plasma that matched the script remarkably well, including the slight tilt from perfect scale invariance. Planck collaboration, 2018. You visualize those peaks as a string of mountain lakes reflecting starlight, evenly spaced but not identical. The heights telling you about the early soup's density, composition, and expansion history. Inflation also suggests a background of primordial gravitational waves, ripples of space-time itself, that would leave a subtle curl, the so-called B mode, in the polarization of the afterglow. Instruments have hunted that curl and, so far, found strong upper limits. The quiet is itself a clue to the energy scale of inflation's wind, hinting that if those waves exist, they are shy. Planck collaboration, 2018. But inflation is not a single painting. It's a gallery. There is new inflation, where the field lingers near a plateau before rolling, and chaotic inflation, where it starts high on a broad hill and drifts downward. Linde, 1982. There are plateau models, hilltop models, natural inflation with periodic potentials, and star-shaped options that give similar tilts but different gravitational wave promises. You pace the gallery slowly, hearing your footsteps echo. Each canvas has a frame, the potential shape, and the frames can be tested by how steep they are and how smoothly the field rolls. You rest your fingers on one frame and feel cool wood. The beauty here is that variety lives under a common principle, like many rooms in one house. Still, doubts belong in the house too. Some worry about initial conditions. Does inflation itself require special tuning to start? Others debate the spectre of eternal inflation, quantum fluctuations so large in some patches that expansion never ends globally, creating a multiverse in which pockets like ours stop inflating and heat up, while elsewhere the wind continues without end. You feel that idea as a vertigo with velvet ropes, a museum that keeps adding new rooms beyond the map. It is mathematically plausible in many models, but philosophically dizzying. The right move tonight is to note both the explanatory power and the open doors. Inflation explains a lot with a little, and yet it invites careful, testable criticism. Maybe the universe just loves to repeat patterns. A rule that is generous enough to spawn many rooms, yet strict enough that some wallpapers are disallowed by the data. You close your eyes and sense the smoothing directly. Before the wind, space is a quilt puckered by irregular stitching. During the wind, it flattens under a warm iron. Stitches stretching, puckers easing. After the wind, it cools, now ready for the delicate embroidery of atoms, stars, and time. You recall the freckles in the afterglow and realize you've met them twice. First as quantum shivers, then as acoustic ripples, then as galaxies, and finally as you, listening. The continuity comforts you. Inflation is not a detour. It's the bend in the river that makes the next valley possible. As you drift toward the next section, where those quantum jitters grow into the blueprint of structure, you keep one number in your pocket. Enough E-folds. Around 60 gives time for smoothing, for horizon solving, for flatness ironing. You don't need the exact count to feel the gist. You just know that the wind blew long enough and gently enough to make our sky's evenness plausible and its freckles precious. The room is quiet. Your heartbeat slows to match a universe whose wildest rush happened long ago, whose calm today is an artifact of that rush. You smile at the paradox. Haste made stillness. Somewhere, perhaps, the fabric still hums with the memory of that breath, like a drumhead at rest that knows the song it once carried. You lean into the quiet, left by inflation's wind, and discover that the silence isn't empty. It's speckled with whispers. The room of space seems still, yet in that stillness you hear a high, breathy hiss, the sound of quantum ripples, too soft to ruffle a feather, being stretched until even galaxies will someday notice. In the language of fields, nothing is ever perfectly flat. The inflaton and the space-time it rides on quiver with zero-point jitters. During inflation, those jitters inflate too, ballooning from subatomic tremors to horizon-sized undulations, frozen as slight variations in density, the first sketch of where matter will gather and where it will give way. Bukhanov and Chibisov, 1981. Hawking, 1982. You picture a pond at night. The surface looks black and calm until moonlight reveals a lace of ripples. Here the moonlight is expansion itself, drawing faint ripples into relief. Each ripple begins smaller than an atom, a vibration of the quantum vacuum. Because space expands so rapidly, a ripple's wavelength outruns the causal neighborhood. The co-moving horizon slips outside and can no longer oscillate. It pauses like a breath you hold while listening. That pause, paradoxically, preserves the fluctuation as a fixed imprint in the curvature of space-time, a gentle hill or hollow awaiting gravity's later hand. Hawking, 1982. Starobinsky, 1982. You feel one such hill beneath your feet now, not steep enough to stumble, just enough to know you're standing somewhere particular. There is a simple, durable promise in this mechanism. Scale invariance. Almost. Because inflation treats many sizes, similarly stretching all wavelengths by nearly the same factor, the spectrum of ripples is close to flat. You get comparable power on many scales, with a slight tilt that tells you the inflaton wasn't perfectly steady, but slowly rolling. Mukhanov and Chibisov, 1981. You roll that idea in your palm like a coin minted with a near-perfect circle and the faintest eccentricity. Later, satellites will measure that tilt in the sky's afterglow and nod in recognition. For now, you let the logic settle. Quantum randomness made big, then saved by expansion's freeze. The mathematics behind the hush has a name with a heartbeat, the Mukhanov-Sasaki variable, a clever combination of field and geometry that lets the equations sing in a single voice, like two choir sections tuned into one note. You don't need the formula tonight. You need the feeling how the variable's equation looks like a familiar harmonic oscillator, whose frequency changes with cosmic time, crossing a threshold when wavelengths exceed the horizon scale. Before crossing, you you hear quick trills. After crossing, long-held notes that stop vibrating. The universe is composing its overture by letting instruments fall silent in just the right key. Mukhanov and Chibisov, 1981. You listen for the character of these notes. They are adiabatic. All components, photons, baryons, dark matter, share the same fractional over or under density, as if the orchestra swells and subsides together rather than trading solos. They are nearly Gaussian. The statistics of their heights and hollows follow the gentle bell curve of chance, a sign that many small independent jitters added up without one bully fluctuation taking over. You picture snowflakes landing on a windowsill, each unique, but together making a smooth drift, and they are coherent. Phases lined up so that when the primordial plasma later rings compression and rarefaction, the echoes make crisp acoustic peaks in the microwave sky. Those peaks, like evenly spaced ripples on a drum skin, will become the most delicate fingerprint of this early music. Hawking, 1982. You step closer to one ripple's life story. It's born deep inside the horizon, oscillating briskly like a violin string. Inflation stretches it until one moment its wavelength equals the horizon size. Crossing that threshold is like walking from city noise into a cathedral. The echo changes, the note lingers. Outside the horizon it freezes, its amplitude fixed by the energy scale and the speed of the roll. Time passes. Inflation ends, reheating floods the world with particles, and the horizon grows again. The ripple re-enters, now as an initial condition for sound waves in the photon-baryon fluid. Where it was a hill, gravity pulls. Where a hollow, pressure pushes back. Together they set up a rhythm that leaves bright and dark rings in the microwave background, and later a faint preference for galaxies to be separated by certain scales. You trace this arc with a fingertip and feel the continuity. A single hiccup stretched into a cosmic drumline. Starobinsky, 1982. There is a sensory image for their tininess. Imagine tasting a soup so perfectly blended that only, every so often, a single grain of salt brushes your tongue. The ripple's amplitude is that subtle, 1 part in 100,000 in the afterglow's temperature. Yet from those delicate grains, gravity will cook stars and you. Maybe the universe just loves to repeat patterns. Soft seeds becoming sturdy trees, whispers growing into choruses, small causes growing into large meanings. You turn your ear for alternative melodies because good science listens wide. Quantum ripples do not have to come from a single, simple, slow-roll field. Multi-field models add isocurvature modes, relative fluctuations between components that could sway the pattern, features in the potential kinks. Plateaus could imprint wiggles in the power spectrum. Some scenarios predict a touch of non-Gaussianity, a skew or a triangle in the statistics that would betray richer dynamics. Each possibility is a different instrument the sky might reveal or rule out. Each has a sound you could, in principle, learn to recognize amid the hiss. So far, observations keep pointing back to the clean, nearly Gaussian, nearly scale-invariant tune, like a critic who keeps awarding the same patient sonata. Best in show, Hawking, 1982. You imagine touching a ripple. Under your hand it feels like silk laid over velvet, smooth at first, then giving way to a soft depth. That depth is gravity's promise. In dark matter's invisible presence, overdense regions pull harder and grow. Underdense regions empty and widen. The blueprint the quantum jitters left is faithful but not final. It invites gravity's centuries-long dance. Later, gas will cool in the wells, igniting stars. Supernovae will blow bubbles. Black holes will stir the pot. But the broad strokes, filaments, clusters, voids, will still trace that first pattern, like a fresco's sketch lines peeking through centuries of pigment. You let a reflective question take shape as your breathing slows. How strange, that uncertainty. The principle that limits what you can know about a particle's position and momentum becomes the thing that lets you know how the largest structures came to be. The thing that hides details in the laboratory reveals blueprints in the cosmos. Maybe the universe keeps accounts fairly. What it withholds in one ledger, it returns with interest in another. Before you leave, you run a fingertip around the rim of possibility. Primordial gravitational waves, if scalar ripples, the ones that change density, come from quantum jitters, so could tensor ripples transverse shivers of space-time itself. Their amplitude would sketch the energy scale of inflation, their telltale curl a faint scribble in the afterglow's polarization. Instruments haven't caught that curl yet, only tightening the leash, but you keep the image anyway. Frost-delicate crescents written across the sky, a signature of the universe's earliest breath. Whether the crescents appear or not, the scalar story remains steady and bright. Quantum notes carried out of the tiny and into the everywhere. Hawking 1982. As you drift onward, the hiss softens into a map in your mind. You see dots and filaments budding from the ripples, like constellations growing bones. You remember a line from earlier: haste made stillness and add a companion. Randomness made order. You tuck both into your pocket. The room is cool. The stars outside the window feel close. Somewhere, a microwave photon last scattered 13+ billion years ago. And now, finally, brushes a detector on Earth. It carries the faintest accent of those quantum ripples. A rumor made good. You smile in the dark, reassured not by certainty, but by the coherence of the song. You open your palms and catch heat, not the warmth of a campfire, but a brightness that feels like pressure, a light that pushes back. The room you stand in is not a room at all. It is the early universe as a single, radiant soup, thick with particles that don't yet know the quiet of atoms. Quarks swim in schools. Gluons stitch and unstitch their bonds like lightning-fingered tailors. Electrons and positrons wink into being and out again. Photons ricochet so quickly that distance loses its ordinary meaning. The air, if you could call it air, smells like hot metal and ozone in your imagination. And somewhere beneath the glare you hear a high, glassy hum. The sound of matter in thermal equilibrium, everything sharing energy, as if by unanimous agreement. Kolb and Turner, 1990. You float at a moment when the expansion is young and decisive. Radiation rules the dynamics. Pressure is a third of the energy density. So the equation of state is W equals 1 divided by 3, and the universe breathes according to that rule. Scale factor growing like the square root of time, temperature falling as the inverse of size, except when small dramas tweak the curve. Kolb and Turner, 1990. You can feel that rule as a bodily rhythm, a long exhale, a soft, measurable cooling that never stalls. In this era, numbers matter because they paint sensation. A microsecond. After reheating, the temperature is around 1 trillion Kelvin. The quark-gluon plasma has the texture of a storm. Nothing binds for long, yet the crowding is so relentless that free is a relative word. You imagine dipping a spoon and feeling the broth shove back. As the seconds tick, cosmic heartbeats you cannot hear. But trust cooling carries you across thresholds. At roughly 10-6 seconds, the energy per particle slips low enough that quarks find it favorable to lock into hadrons. Protons and neutrons condense like dew from steam. The transition isn't fireworks. It's more like a fog changing grain. A phase change you sense as a shift in viscosity. Suddenly, the soup drags a little differently around your fingers. Degrees of freedom drop. The effective number of particle species sharing the energy, G*, shrinks. Entropy reassigns itself, but remains conserved overall, so the expansion and cooling keep their pact. Kolb and Turner, 1990. Maybe the universe just loves to repeat patterns, wild collectives settling into sturdier, quieter bonds. A moment later, in cosmic bookkeeping, about 1 second neutrinos decouple. They were once part of the chatter, exchanging energy with everything else. Now the interaction's thin. The mean free path grows, and they drift off with their own thermal story, a ghostly sea that will still stream through you tonight by the trillions without a sound. You feel their departure as a sudden hush at the edge of hearing, like guests slipping out a side door from a crowded hall. Kolb and Turner, 1990. Their temperature will trail the photons after electron-positron annihilation. The ratios lock in, an invisible ledger that will matter for the light element yields, and the expansion rate itself. Electrons and positrons still plentiful, keep the photons tightly leashed. Thomson's scattering is efficient, and the mean free path of light is a tiny fraction of the horizon. You pass your hand through the imagined plasma and feel a grainy resistance, as if moving through sunlit honey. In this baryon photon fluid, pressure is high. The speed of sound is about c, square root 3, and any compression triggers an elastic pushback. You remember the quantum ripples we froze earlier. Now they return as acoustic waves, ringing through the soup. The music is not yet visible, but it is there. A pattern of pressure, crests, and troughs that will one day write peaks into the sky's afterglow and a preferred galactic spacing into the cosmic web. It's comforting to recognize an old friend in a new mood. The same ripple that was a whisper in inflation is now a drumbeat in the plasma. Thermodynamics is the quiet ruler here. Equilibrium distributions. Fermi-Dirac for fermions, Bose-Einstein for bosons set the counts. Reaction rates compared to the Hubble rate decide what stays coupled and what falls out. You keep the heuristic in your pocket. If collisions happen faster than the universe doubles in size, the species stays in the conversation. If not, it drifts into silence. That simple contest rate versus expansion writes the timeline of the early cosmos. Kolben-Turner, 1990. It's almost domestic in its simplicity. Who can keep up with the group text, and who mutely watches the messages scroll by? A few seconds in, the temperature dips below the rest mass of electrons. Pair annihilation surges, positrons meeting electrons in brief. Perfect cancellations that flood the photon bath with energy. You imagine a soft rain of sparks melting into daylight. Photons win, and their number density swells relative to baryons, locking in the famous 10 billion to 1 ratio that will later make photons a luminous majority and matter a rare spice. Kolben-Turner, 1990. The sensory image is brightening. The soup glows more fiercely even as matter content simplifies, like a kiln flaring as the clay sets. Through all of this, protons and neutrons carry a quieter drama. Their ratio, set by the competition between weak interactions and expansion, begins near unity at the highest temperatures, but slides as neutrons are slightly heavier. By the time the weak interactions freeze out, around 1 second and a few billion Kelvin, neutrons are already less common. Some decay in the minutes that follow. This balance, so sensitive to timing and temperature, is the preface to the next act, primordial nucleosynthesis. You can feel the stakes rise gently, a softer gravity drum, a quicker heartbeat of reactions. You keep your voice low, knowing we'll enter that forge soon. Between seconds and minutes, the universe is still too hot for nuclei to hold together confidently. Deuterium, the fragile stepping stone nucleus, is photodissociated almost as soon as it forms. This deuterium bottleneck is a patient gate. Only once photons soften enough, around a few minutes and roughly 9 Kelvin, can deuterium survive and the chain to helium and light elements proceed. You feel the bottleneck as a sticky turnstile in a crowded station. Once it clicks, flow begins. You hold back from stepping through we will in the next section, but you rest your palm on the cool metal and sense the imminent surge. Kolben-Turner, 1990. Pause with the plasma itself. It is tightly coupled, conductive, and opaque. If you shine a flashlight, humor me, the beam doesn't lance forward. It dissolves instantly into the crowd, scattered into sameness. The concept of inside and outside is soft because everything is connected by quick exchanges. Entropy per co-moving volume stays constant. The universe is an excellent accountant, tallying disorder precisely as it moves from one chapter to the next. And yet, within the sameness, the small differences we cherished, the 1 in 100,000 ripples are preserved and gently amplified. Pressure and gravity debate in every region. Neither shouts, and the result is graceful. Sound waves of many wavelengths, phases aligned, each awaiting the moment the fog will clear so their pattern can be seen as temperature freckles across the sky. You tilt your head and listen to the fluid's voice. It has a vowel-like resonance, long and rounded. Compression raises temperature and pressure. Pressure pushes back, causing rarefaction. Rarefaction makes room for gravity to tug again. The cycle continues, a breathing you can almost mimic with your own chest. In, out, in. You measure the breath by a standard yardstick, the sound horizon, the distance those waves can travel before the photons let go. Later, that yardstick becomes a ruler in the galaxy map, a subtle 150 megaparsec preference in how far apart clusters like to be, a cosmic metronome that lets cosmologists keep time across billions of years. The idea feels like a gift you unwrap twice, first as plasma music, then as a fossil rhythm in the late universe. Reflect for a moment in the glow. You are made of particles that once knew this crowd intimately. Your atoms are slow conversations compared to this early shout, but they inherit its terms. Conservation laws, symmetries, balances struck under pressure. Maybe the universe just loves to repeat patterns. Equilibria reached, then gently broken. Bonds formed, then made into scaffolds. Noise averaged, then turned into signal. The poetry isn't an escape from accuracy. It's a way of remembering it. The way a melody helps you keep a formula close without clutching the symbols too tightly. As the plasma epoch stretches toward its long afternoon, the photon baryon fluid remains coupled for hundreds of thousands of years. Gravity tries to gather, pressure resists, the dance repeats. Electromagnetic interactions enforce togetherness. Coulomb forces lock baryons into the sway of photons. Dark matter, immune to the electromagnetic shout, begins quietly building the skeleton of structure beneath the luminous fog. It is a two-tiered choreography, a visible ringing surface and an invisible, gathering depth. You feel both one as a shimmer on your skin, the other as a firming floor beneath your feet. The rule of thermodynamics guides you out. Temperature falls, interactions thin, complexity simplifies, then recombines into new forms. You carry forward the constants that matter: the photon's dominance, the baryon to photon ratio, the neutrino background's cool whisper, the sound horizon's growing chord. Ahead lies the first real chemistry of the cosmos. Light elements forged in minutes from this heat, their abundances stamped into time like hallmarks on silver. For now, you let the soup's brightness fade a little in your mind and notice that, even in such extremity, the universe is calm in its arithmetic. It is loud, yes, but not frantic. It is busy, but not hurried. It makes room for you to breathe in time with it and wonder how a world so violent to the eye can be so composed in the ledger. You step through the deuterium turnstile we touched a minute ago and feel the hallway widen into a workshop. Quiet, efficient, hot enough to glow but cool enough to build. Minutes have passed since the universe's first breath. The light in here is white with a hint of blue, like a kiln door cracked open. The air of imagination smells faintly of solder and rain. In this brief window, call it from about 10 seconds to 20 minutes, the cosmos practices its first chemistry. It forges light elements, mostly helium-4, with a dusting of deuterium, helium-3, and lithium-7. The steps are simple, the consequences vast, and the recipe has stayed the same in our equations since the mid-28th century, when a trio with a sense of humor signed the primordial menu alpha, beta, gamma, alpha, beta, and gamma outlining how a hot Big Bang could synthesize the lightest nuclei. Alpha, beta, and gamma. 1948. You hold the ingredients, protons and neutrons, in a ratio set earlier by weak interactions and the clock. When the temperature dropped to around a few billion Kelvin and the expansion outran the weak force, neutrons stopped easily, turning into protons and vice versa. Neutrons are slightly heavier, so the ratio tilted in favor of protons, then tilted further as free neutrons decayed. By the time the deuterium bottleneck finally opens roughly at a temperature of 0.1 MeV, a couple of minutes in, you have just enough neutrons left to matter. You feel them like a sparse scattering of cool pebbles in a warm stream, each one precious, each one destined to be captured into something longer lived. The first bond is the hardest. A proton and a neutron meet, and, if the photon fog isn't too harsh, form deuterium, one proton, one neutron, a nucleus held together by a modest glue. Before this moment, the photon bath is fierce. High-energy photons are so abundant that any deuterium formed is almost immediately shattered. That is the bottleneck. Conditions must soften enough that the breakers diminish, and the builders can keep what they make. When the door swings open, you hear a shift in the room's sound, less crackle, more clink as P plus N, D plus gamma begins to stick. Steigman, 2007. Once deuterium survives, the workshop speeds up. Deuterium fuses with deuterium to make helium-3 or tritium. Deuterium fuses with helium-3 to make helium-4 and a proton. Deuterium with tritium yields helium-4 and a neutron. It's a short ladder, but each rung clicks cleanly in the heat. You sense a growing roundness in your hands, the helium-4 nucleus, 2 protons and 2 neutrons, alpha-tight and stubbornly bound. Physics loves this nucleus. It's unusually stable, with a binding energy that makes it a favored endpoint for the early chain. In a few minutes of cosmic time, Most available neutrons are locked inside these quartet shells, and the room fills with the soft, noble weight of helium. Steigman, 2007. There is beauty in the numbers. The mass fraction of helium-4, how much of the ordinary matter's mass ends up as helium, settles near 25%, not 5%, not 80%, but a quarter, with small variations depending on the exact expansion rate and the neutron lifetime. You imagine a silver stamp on the universe's first ingot, He4 to 0.25 by mass. Deuterium, more fragile, remains as a trace, parts per 100,000 relative to hydrogen, yet that trace becomes a sensitive gauge of the cosmic baryon density, because any later stellar processing tends to burn deuterium away rather than make it anew. Helium-3 lingers less abundantly. Lithium-7 appears in stubborn sprinkles through pathways like helium-3 plus helium-4 beryllium-7, which then captures an electron later to become lithium-7. You run your finger over these yields as if over braille, each bump a story, each story a test. Steigman, 2007. The tests are exacting. Big Bang nucleosynthesis, BBN, is a one-parameter theory at heart. Give it the baryon to photon ratio, the cosmic recipe's richness, and it predicts the primordial light element abundances. When astronomers measure deuterium in distant, nearly pristine gas clouds backlit by quasars, or helium in metal-poor dwarf galaxies, they find numbers that line up with the BBN ledger and with the cosmic microwave background's independent accounting of baryon density. 2 chapters, same tally, written billions of years apart. You hear the satisfaction as a soft chord resolving. Steigman, 2007. But the music includes a minor key, the lithium problem. Some observations of old stars in our galaxy show less lithium-7 than vanilla BBN predicts for the baryon density inferred from the microwave sky. Is it stellar depletion, nuclear rates, or new physics affecting the early expansion or particle content? The question sits like a small, glinting stone you can't dislodge with your toe. It's not a crisis for the whole symphony, but it is a note that keeps you honest. Nature's score has annotations we still need to read. Steigman, 2007. Feel the dependencies like dials under your fingertips. Turn the baryon density up and deuterium goes down. More crowding means deuterium is processed more efficiently into helium. Turn the expansion rate up, say, by adding extra relativistic species, more light degrees of freedom, and the universe races through the window faster. Neutron to proton ratios freeze higher, leaving slightly more neutrons to be captured, nudging helium-4 upward. These are not abstractions. They're sensitivities that let BBN act as a detector for hidden actors in the early stage, a way to weigh ghosts by their gravitational footprints on timing and temperature. Steigman, 2007. The sensory picture steadies you. The workshop's light is still too bright to stare into, yet you can taste the metallic tang of newborn nuclei cooling in the cosmic breeze. You cup helium 4 inches your hands and it feels round and sealed, like a marble smoothed by a river. Deuterium feels more delicate, like a soap bubble that demands calm breath. Lithium-7 is a grain of salt on the tongue, rare, distinct, slightly bitter. Maybe the universe just loves to repeat patterns. Fragile beginnings, opening gates, then quickly giving way to sturdy forms that anchor what comes next. You trace a callback to our earlier sections and smile. The ripples born as quantum whispers, stretched by inflation, now modulate these reaction rates, locally tiny overdensities, run a hair warmer, underdensities, a hair cooler. But the overall outcome is a triumph of homogeneity. Across horizons, in every direction, the universe prints the same helium stamp, the same deuterium signature, with deviations too small to scratch the gloss. Later eras will fracture this sameness into stars, but here, in the minutes that set the table, fairness rules, and then the fire quiets. As expansion continues, the temperature falls below what fusion demands in free space. The workshop shutters itself, not with a slam, but with a satisfied sigh. Further synthesis must wait for the pressure cookers of stars, where gravity rekindles fusion and climbs the periodic table beyond lithium. You step back from the bench and look at what's been made. A sea of hydrogen with islands of helium, tracer currents of deuterium and helium-3, occasional flecks of lithium-7. You realize you have just watched the universe decide the bulk chemistry of everything to come. How bright stars will burn, what colors nebulae will glow, how planets will inherit their air and water, a final thought slows your breathing. We often speak of complexity as something that arrives late, as if the early universe were only noise and heat. But the minutes of primordial nucleosynthesis are a kind of quiet competence, a poised moment when conditions are tuned just enough to favor bonds but not chaos. The laws are simple, the outcomes robust, and yet the meaning is intimate. The helium in your lungs when you laugh on a birthday balloon, the deuterium in the ocean you taste on your lips after a swim, the lithium guarding the mood currents in a human brain each carries the timestamp of this furnace. Maybe the universe just loves to repeat patterns. Brief windows opening, simple rules playing out, humble leftovers becoming the scaffolds of wonder. You feel the plasma's grip loosen like fingers unclasping from your sleeve. The bright, crowded soup you've been wading through photons, ringing baryons like an impatient orchestra, cools to a threshold where a new word earns its meaning. Neutral. Electrons, frantic for eons in cosmic baby time, finally settle into orbits around protons. Hydrogen appears not as a color but as a permission. Light no longer scatters at every step. In this moment, about 380,000 years after the beginning, at a redshift near 1,100, the universe does something quietly revolutionary. It becomes transparent. Photons decouple. Darkness falls not because light vanishes, but because it ceases to be trapped in the fog and streams into a deepening night. Peebles, 1968, Zeldovich, Kurt, and Sunyaev, 1969. You know the trigger by feeling for a balance. As the temperature slides below a few thousand Kelvin, the odds finally favor capture over collision. The Saha-like accounting, no equations tonight. Only logic says the energy of the photon bath is no longer fierce enough to keep prying electrons away from protons. Recombination proceeds, not in a snap, but in a soft, thick sunrise of neutrality that washes across the cosmos over tens of thousands of years. The visibility function, the chance a photon lasts scattered at a given time, peaks and then fades. You picture a broad, glowing shell around you, the last scattering surface, neither razor-thin nor sloppy, a luminous rind from which nearly all the microwave photons you will ever measure begin their long, straight flight. Peebles, 1968. The sensory change is immediate. Where before light felt like sunlit honey resisting your hand, now it feels like cool evening air. The mean free path, once tiny compared to the horizon, jumps to cosmic scales. Photons that scattered billions of times now take one step and are free. You listen. The bright clamor of acoustic waves in the photon-baryon fluid fades into a final chord, frozen into temperature patterns that will remain on the sky like delicate frost. The sound horizon we met earlier, the distance those waves traveled before freedom, hardens into a ruler, etched across the afterglow, and much later, echoed in the galaxy map. You hold that ruler and it feels notched and trustworthy, a yardstick you can carry anywhere. The physics has texture you can trust. Neutral hydrogen's formation reduces free electrons. Fewer electrons mean a smaller Thomson scattering rate. A smaller rate means photons slip through. Yet the last word belongs to a bottleneck we've learned to expect from this universe. Lyman alpha photons, those released when electrons drop into the ground state, are easily reabsorbed. Recombination must borrow a side door. 2-photon decay from the 2-second state. A rare but decisive channel that lets neutrality finish its work. The detail is exquisite to theorists and invisible to the eye, yet you sense it as a soft whisper in the mechanism. The way a tiny spring in a clock makes all the gears keep time. Peebles 1968, Zeldovich, Kurt, and Sunyaev 1969. Just as the light lets go, something else becomes heavier in spirit. Baryons, no longer lashed to photons by constant scattering, fall more eagerly into the dark matter's waiting wells. The acoustic oscillations end, inertia and gravity take over. You feel yourself sink a millimeter in the floor, as if the room itself bowed slightly toward hidden masses below. The pattern seeded by quantum jitters and sculpted by plasma music is now the initial condition for structure's long, quiet crescendo. Dark matter keeps time. Gas will follow, cool, and later ignite. The afterglow preserves the overture. The rest of the symphony begins in darkness. Darkness here is rich, not empty. You look out across a universe with no stars yet, No galaxies to speak of, only neutral hydrogen and helium, drifting through a night that deepens as expansion stretches every wavelength. The photons that just decoupled redshift from fire to embers to invisible radio. Their spectrum stays nearly a perfect blackbody, now at 2.725 K, a temperature like frost in a deep cave. If you tilt your head, you can hear them in the mind's ear as a uniform hiss, with tiny rises and falls 1 part in 100,000 mapping the early ripples we've followed for 4 sections now. That map becomes the most precise baby photo ever taken. The Cosmic Microwave Background, CMB, measured in loving detail by Kobe, WMAP, and Planck collaboration, 2018. You touch the photo's texture. The temperature freckles are not random freckles. They arrange into acoustic peaks in the angular power spectrum, each peak the fossil of a favorite drumbeat in the primordial fluid compression here, rarefaction there. The first peak, proud and high, marks the sound horizon's angular size. Subsequent peaks tell you about baryon content, dark matter share, spatial curvature, and more. Polarization, to a faint alignment of last scattered light, adds its own filigree, a clean E-mode pattern born from the same scattering geometry that makes Earth's skies blue at dusk. Even the slight smearing of power on small scales, silk-damping whispers of the final diffusion of photons before freedom. A blurring you can feel with your fingertips like chalk, dust smudged across a slate. Hu and Dodelson, 2002. Planck collaboration, 2018. There is a second act to the sky's story. Later, the first stars and galaxies will reionize the hydrogen, rekindling, scattering just enough to nudge the CMB's large-scale polarization and dim the smallest temperature contrasts. That reionization optical depth is a postscript, not a rewrite, a light fingerprint of the universe's teenage years upon its baby portrait. For now, let the portrait stand. A nearly perfect blackbody with an exquisitely patterned speckle that encodes age, geometry, and ingredients. You breathe slower, the way you do in a museum when a single painting holds much of a room. You look back once more at the moment of decoupling and notice how many threads converge there. The baryon to photon ratio fixed earlier shapes how rapidly neutrality completes. The expansion rate sensitive to the radiation content, including the quiet sea of neutrinos, sets the timing of recombination's fade and the width of the last scattering surface. The inflationary ripples we rode in sections 3 and 4 choose which regions are a touch denser or rarer, and thus a touch warmer or cooler on the sky. The plasma acoustics from section 5 stamp an overtone structure that Planck will later read like a barcode. Peebles, 1968. Planck collaboration, 2018. The coherence makes you smile. Separate chapters, one story. A small, earnest philosophy arrives uninvited and is welcome. Maybe the universe just loves to repeat patterns. Fog to clarity, coupling to freedom, noise to signal. The same arc plays in human hours, learning to ride a bike with a parent's hand on the seat, then gliding alone into the evening. Photons do that on a cosmic scale. They practice in the crowd and then ride free, carrying with them a record of the crowd's rhythm. You stand very still and imagine a single microwave photon leaving the last scattering surface. A tiny arrow of warmth set upon a path without another touch until it kisses a detector. Its journey is long enough that entire continents will rise and fall beneath the future instrument, long enough that languages will bloom and fade between its departure and arrival, yet it keeps faith with the physics of its launch. When it reaches us, it contributes one whisper to a chorus from which we infer the universe's age about 13.8 billion years, its composition roughly 5% ordinary matter, 27% dark matter, 68% dark energy, and its geometry so close to flat that space feels Euclidean beneath your feet. Planck collaboration, 2018. You feel humbled, not by size but by coherence. And then the room darkens in a way that invites stars. The dark ages begin, a long, patient interval when gravity gathers, gas cools, and the first lights kindle. Decoupling wasn't an end, it was a clearing of the stage. The orchestra has left you with sheet music written in temperature and polarization. And now, in the hush, new instruments tune up in the wings. You take one last breath of the clean, neutral night and tuck the ruler of the sound horizon back into your pocket. Ahead, ripples will become galaxies. Brightness will return in points rather than fog. For now, let the darkness fall. It is fertile, and it remembers. You hold the afterglow like a cool shell at your ear, and hear not ocean but origin. The speckles on this shell, those tiny temperature freckles scattered across the whole sky, look like noise at first, like the static of an untuned radio. But you lean closer, and the static reveals rhythm. It is the map we promised. A portrait of the infant universe, painted in microwaves, telling you its age, its shape, and the measures of what fills it. You turn the shell slowly, and the light seems to breathe a faint patch here, a whisper warmer, there a breath cooler, 1 part in 100,000, no more. Yet from this snowfall of nearly uniform brightness, the cosmos divulges its autobiography. Planck Collaboration, 2018. Your fingertips trace the lineage of maps. First, the brave blur of Kobe, a coarse mosaic that, for the first time, showed structure real anisotropies, not artifacts etched across the microwave sky. It also weighed the spectrum with a jeweler's scale, and found it a near-perfect blackbody, the most precise thermal curve measured in nature, a seal on the hot Big Bang's furnace, Smoot et al. 1992, Mather et al. 1994. That felt like hearing a single, pure note in a noisy hall. Then WMAP sharpened the lines, filling the room with melody, its decade of data resolving acoustic peaks and valleys with grace, and confirming that the universe is remarkably flat and old in a specific way. Bennett et al. 2013. Finally, Planck arrived with a violinist's precision. Temperature, E-mode polarization, and lensing reconstructed to exquisite detail. A map so fine you can see not only the freckles, but the faint smudge of matter bending light across them. Planck Collaboration, 2018. The arc from blur to lace is a small miracle in patient measurement. The physics beneath the freckles is the drumline we've been following. The primordial plasma rings with sound before recombination. Those waves imprint their favorite notes at the last scattering. If you take the full sky map and compute how much structure appears at each angular scale, you get a score, the angular power spectrum whose first peak tells you the angular size of the sound horizon, the very distance those waves traveled before photons slipped free. You feel that peak as a mountain you can lean against. Its position, near 1 degree, says space is very nearly flat. Triangles in our universe add up the way Euclid taught, not like a saddle or a sphere. Bennett et al. 2013. Planck Collaboration, 2018. The heights of the next peaks, alternatively tall and short, reveal how baryons weigh on the waves. Heavier matter makes stronger compression peaks and softer rarefactions, letting you weigh ordinary matter with surprising intimacy. The overall envelope of power on small scales, diminished by diffusion, whispers of photon wandering just before freedom. The chalk dust blur called silk damping. Polarization adds filigree. Scattered light acquires a delicate alignment, and the pattern mostly E-mode. The gradient-like weave provides a second, independent way to read the same acoustic script and to time recombination and reionization. You run your fingers over the polarization map, and it feels like fine linen stretched taut, the threads aligned just so. B-modes, the curly counterparts, remain quiet at these energies, save for the swirl induced by gravitational lensing, itself a measure of the matter web between us and the last scattering. Even that swirl is useful. By de-swirling the map, you can learn the mass distribution along the way, a soft, tactile sense of the invisible scaffolding we met in the dark Planck Collaboration, 2018. From this music, parameters fall into place with a satisfying click. The age. About 13.8 billion years, inferred from how fast space expands today and how the peaks arrange themselves in size and spacing. Planck Collaboration, 2018. The ingredients, roughly 5% ordinary matter, 27% dark matter, 68% dark energy, figures cross-checked by the relative peak heights and lensing blur. The Hubble constant, the present-day expansion rate, emerges from the same web of relations tied to the sound horizon, the matter content, and the angular pattern. Even the number of light, relativistic species, neutrinos, and any cousins that behave like them, leaves a faint signature in the damping tail and the early expansion rate, a clue written in the thickness of the frost. You feel the numbers not as digits but as weights in your palm, oddly reassuring. You look for cracks, because the best maps invite skepticism. One puzzle lives in the contrast between early and late-time inferences of the Hubble constant, a tension between values derived from the afterglow's clean geometry and values measured from the nearby universe's supernovae and ladders of distance. The map does not resolve the tension on its own. It simply holds its line with remarkable consistency. Planck Collaboration, 2018. Another set of tests comes from comparing the CMB-inferred baryon density to deuterium abundances in ancient gas. Two very different thermometers, same temperature, and they agree within tight uncertainties. Bennett-Ailey, 2013. Where agreement persists across methods, confidence deepens. Where discrepancies arise, curiosity sharpens. Maybe the universe just loves to repeat patterns. Harmony punctuated by a single, intriguing discord that keeps us listening for an encore. The sensory richness of the map is easy to forget in the numeracy. Imagine the whole sky as a faint, mottled parchment. The hottest spots are warmed by compressions, like the squeeze of a drumhead. The coldest by rarefactions, spaces where matter and light briefly gave each other room. Magnifying the parchment, you see the lensing, the smudge and shear from intervening mass like a subtle pucker where a heavy coin pressed beneath the paper. You tilt the parchment, and polarization threads catch the light, crossing in quiet diamonds. It is data, yes, but it is also texture, a tactile history you could almost read with closed eyes. You return to the instruments, those careful ears of the sky, Kobe's DMR, WMAP's differential radiometers, Planck's HFI and LFI, each built to be quiet in their own noise, each cooled, shielded, and calibrated until the universe's whisper was the loudest thing they heard. Firers on Kobe weighed the CMB spectrum so precisely that any deviation from blackbody was constrained to 1 part in 10,000. No rogue energy injections, big enough to scar the curve. Mather et al. 1994. It's like tasting a soup and knowing, with absurd confidence, that no cook added a handful of chili after the first simmer. The discipline of that knowledge is as beautiful as the poetry we sing over it. You let the implications widen. A flat universe implies a particular story of total energy density. Peaks that match theory argue for adiabatic, nearly Gaussian initial conditions. Polarization timing pins down when the first stars rekindled scattering. The CMB thus triangulates epochs. The first 380,000 years in detail, the minutes of nucleosynthesis by matching baryons, and the later billion years by the gentle fog of war reionization imprinted on large scales. The map is not merely a snapshot, it is a hinge connecting chapters. You recognize the pattern we've leaned on, micro to macro, mechanism to meaning, and you feel at home. Pause and listen to a single pixel. It contributes almost nothing to the grand statistics. Yet without countless such pixels, no peaks would stand, no parameters would settle. The lesson is humble and human. Large truths often ride on small, patient accuracies. Maybe the universe just loves to repeat patterns, freckles into faces, whispers into songs, errors into understanding, so long as we keep our instruments tuned and our questions gentle. You close your eyes, and the afterglow continues behind your lids. A dim, even warmth. In that warmth is a ruler you can carry to galaxies, a clock you can set in clusters, a compass you can hold up to dark energy and ask it to reveal its pressure. The map in the afterglow is not an end, but a reference, a quiet standard to bring to louder places. When you open your eyes, the room seems a little steadier, as if the ceiling knows it spans a flat space. You tuck the parchment away, confident that whenever you unfold it, the freckles will be where you left them, patient, precise, and full of story. You walk into a room that shouldn't be heavy, and yet the floor bows. Nothing obvious is there, no mountains, no iron statues, only the quiet of intergalactic night. Still, your feet know a pull, subtle but insistent, as if a hand beneath the carpet gathered the threads and drew them into a fist. That hidden grip is the universe's most common substance of the kind you can't see, dark matter. It neither shines nor swallows light the way a black hole does. It simply weighs, it simply gathers, it simply bends the paths that everything else takes. You can't put it in a jar, but you can watch the world behave as if the jar were full. Your first clue arrives with a brisk voice from 1933, echoing through the coma cluster. You join Fritz Zwicky in counting galaxies and clocking their speeds. They zip inside the cluster like bees in a glass hive. By his reckoning, their velocities are too high to be bound by the visible mass alone. The hive should fly apart unless an unseen glue is holding it together. He calls it Dunkel Materie, dark matter, a practical name for a stubborn accounting error that refuses to be explained. Away Zwicky, 1933. You feel the cluster's gravity like a low organ note under a choir felt more than heard. Essential, weighty. Decades later, you ride in the passenger seat as Vera Rubin and Kent Ford trace the rotation of spiral galaxies. Logic suggests the outskirts should turn slowly, stars feeling less pull the farther they are from the luminous center. Instead, the curves go flat. Outer stars whirl nearly as fast as inner ones, as if the galaxy sits inside a fat, invisible halo whose mass keeps rising with radius. You watch the starlight blur into patient arcs on the spectrograph and sense a truth settling in. The light is only the lantern. The hand that holds it is much larger. Rubin and Ford, 1970. The sensory image is of a vinyl record spinning, the label and the rim keeping pace, an improbable choreography unless a hidden ring presses evenly from beyond. You test another sense, sight distorted. Gravity bends light, not metaphorically but literally. Mass curves space-time, and photons follow the curve. Behind a massive cluster, distant galaxies appear stretched, doubled, braided into arcs, gravitational lensing, a glass you can hold up to the sky. Strong lensing is the dramatic version, with arcs like teal ribbons in long exposures. Weak lensing is subtler, a gentle shearing of many background shapes that, averaged carefully, reveals where the mass sits. You imagine running your fingers over a pane of uneven glass and feeling bumps where the view pucker. Mass maps from lensing rarely match the starlight alone. They trace halos not accounted for by gas or stars, cartographies of the unseen. Then, in 2006, one cluster collides with another and the sky offers a clean experiment. The bullet cluster shows a separation. Hot, X-ray, bright gas slams together and sticks in the middle. Galaxies fly through like sparks. But the main mass, revealed by gravitational lensing, passes through with the galaxies, largely unimpeded. The center of gravity and the center of light part ways. The invisible hand refuses to cling to gas the way ordinary matter does, signaling that the bulk of mass is some collisionless component not coupled to electromagnetism. Clauet et al., 2006. You see it in composite. Blue lensing maps offset from pink X-ray clouds, like two ghosts stepping past a puddle while the visible crowd gets mired in it. The feeling is decisive, like a key turning in a lock you've jiggled for years. From these lines of evidence, cluster dynamics, galaxy rotation, lensing your picture ripens. Most matter doesn't radiate or absorb light. It interacts primarily through gravity. Zwicky, 1933. Rubin and Ford, 1970. Clow et al., 2006. But the story is not just about bookkeeping. It's about how structure grows. Remember the quantum ripples you touch, the gentle hills and hollows. In a universe with only ordinary, light-coupled matter, photons would smooth those ripples too well. Pressure would erase small-scale clumps before gravity could amplify them. But with dark matter cold, slow-moving by cosmological standards, overdensities can grow early, well before photons let go. The dark skeleton forms first, patient and invisible. Baryons later fall into its wells, cool, and ignite as stars. You feel it as architecture before ornament, scaffolding before stone. The shape of a halo is not arbitrary. Simulations show a near-universal profile, dense in the center, falling outward, capable of cradling rotating disks and hosting satellite galaxies. Observers weigh halos by their galaxy motions, by lensing, by satellite dynamics, by hot gas in hydrostatic balance. The numbers line up with a sober chorus. Halos are vast, extending far beyond the bright disks we love in photographs. You stand in a dark field and imagine a Milky Way halo reaching hundreds of thousands of light years. A cool, diffuse mass that holds the local group together like a cupped hand. The sensation is of walking at night and realizing the path is lined with unseen trees whose branches touch above you. You listen too for alternative tunes. Perhaps gravity changes on large scales, Mond-like ideas. Or perhaps unseen mass is really mundane but faint. The bullet cluster's offset argues strongly against modified gravity alone. Something that doesn't collide must carry most of the mass. Lensing and dynamics together pin it down. Even if gravity's law gets tweaks, there's still a lot of unseen stuff. The honesty of the inquiry pleases you. Good science keeps the door ajar, but it also installs a draft stopper when data blow too hard the other way. Your senses widen to subtle effects. The CMB we've been holding records how dark matter's gravity deepens potential wells that modulate acoustic peaks. On the way to us, that same afterglow is lensed by the intervening web, its patterns smudged just so. Those smudges let cosmologists reconstruct a map of the total mass, including the dark portion. Galaxy redshift surveys, too, measure a faint preference for certain spacings. Echoes of the sound horizon imprinted on matter, the baryon acoustic oscillation scale, providing yet another ruler that, when compared with the afterglows, fits a model where dark matter is abundant and cold. You run your hand along these rulers and feel the notches match. What is dark matter made of? The room won't say tonight. WIMPs and axions and sterile neutrinos wait in laboratories and observatories. Detectors chilled and shielded to hear a tap from a passing halo particle. Telescopes tuned to catch exotic decays or annihilations. The silence so far is informative. Whatever dark matter is, it is shy in the ways we've asked it to speak. You learn patience from that shyness. Maybe the universe just loves to repeat patterns. The big truths arrive first as gentle pulls and clean maps, and only later as names on a blackboard. Touch the phenomenon once more. You stand behind a galaxy cluster and watch a background galaxy curl into an arc, its light stretched into a smile by mass you can't see. The arc's color is winter blue. Its edge is crisp like a new note on a violin. The cluster's halo feels like a cold wind you sense but cannot see rustle the grass. You walk inside a spiral galaxy and feel yourself held in a grip that doesn't weaken with distance, a steady hand that steadies the disk against the urge to fly apart. The reassurance is paternal and impersonal at once. No malice, no mercy, only law. A final reflection settles like evening. You are made of stardust, yes, but you are arranged by dark matter. Your galaxy, your neighborhood, your long history of star formation, each is nested in a halo that gathered quietly while the visible universe learned to glow. Without the invisible pull, there would be no long-lived disks, no rich clusters, no cosmic web with its filaments and voids. The most present features of the night sky owe their shapes to something that never announces itself in light. It's a good lesson for waking life. Much of what holds us together is not what shines, but what silently keeps time and draws us close. You stand at the edge of a faint hill, a ripple we met when the universe was young, and feel gravity's hand close gently around it, the way mist condenses on a cool glass. Nothing dramatic at first, just patience. The overdensity tugs a little more than the average. Matter drifts its way. The tug grows, the drift quickens. A feedback with no hurry makes a spine, then a sheet, then a thread. Step back, and you see the pattern that Bond once nicknamed the cosmic web. Filaments and nodes woven from what began as whispers in the afterglow. Geometry spun from chance. Bond, Kaufman, and Pogosyan, 1996. Under your feet, the floor becomes corded like rope. In the dark between chords, voids bloom rooms of near emptiness that make the walls stand taller. The physics finds its cadence in two simple regimes. First comes the linear, when overdensities are small and each mode of the pattern grows independently, like 100 piano keys rising together under one slow pedal. Growth is proportional to the scale factor during matter domination. The ripples keep their shapes, only their amplitudes swell. Then, abruptly soft, the non-linear, the moment separate notes begin to harmonize and clash. Peaks merge, valleys evacuate. Local gravity takes command, bending trajectories and mixing scales. You can feel the change, the way you feel the first curl of foam when a gentle wave begins to break. Numerical universes show the transition with visceral clarity. In the Millennium simulation, billions of particles of cold dark matter trace the growth from a smooth early field to a lattice of halos, filaments, and clusters spanning hundreds of millions of light years. Press your palm to that simulated cosmos, and it feels like a wooden relief map. Ridges sharp, basins smooth, halos dot the junctions like polished beads. Springle et al. 2005. The halo's internal structure settles into a near-universal shape steep within, easing without the Navarro-Frank white profile, a pattern that emerges across orders of magnitude of mass, as if gravity prefers a particular curve. Navarro, Frank, and White, 1997. Maybe the universe just loves to repeat patterns. Form follows law, and law finds the same form again and again. Baryons' ordinary matter arrive late to the party but bring the light. Freed from photons after recombination, gas falls into dark halos, shocks, and cools. Where the virial temperature is high and the density kind, gas radiates energy via atomic lines and Bremsstrahlung, slipping inward until it becomes a rotating disk or a spheroidal cloud. Angular momentum, acquired earlier from tidal torques, keeps it from collapsing straight to the center. Instead, it spreads like honey on a plate, thin and luminous. White and Rees, 1978. In lower mass halos, gas can arrive in narrow, cold streams that dive along filaments, threads of nourishment, glowing aquamarine in simulations. A quiet spectacle of supply lines in the dark. Deckel and Bernboim, 2006. You feel those streams as cool currents around your ankles, steady and directional. Then star formation flickers. In the densest pockets, gas fragments, cools further, and crosses thresholds set by turbulence and gravity. The first bursts are blue and brief. The feedback is swift. Supernovae crackle, stirring and heating the gas, sometimes sweeping it from shallow potential wells. In the larger cities of matter, black holes at the centers of galaxies awaken, their accretion disks throwing off winds and jets that can quench or trigger starbirth in an alternating weather of light. Your ear hears it as a hiss and a hush, the room breathing in and out. The details are fierce and local, but the scaffolding is always the same. Dark halos gather first. Gas negotiates its way to the middle. Stars kindle where the gas can linger. Springle, et al. 2005. Across the web, a memory of the plasma's old music survives in stone. The distant sound could travel before decoupling. The sound horizon imprints a slight preference in how galaxies are spaced, a broad bump in their correlation function at roughly 150 megaparsecs. When the Sloan Digital Sky Survey traced millions of galaxies and looked for that echo, it found it. A low drumbeat in the statistics, the baryon acoustic oscillation, BAO scale, the fossil rhythm set in the fog and remembered by the late-time map, Eisenstein et al. 2005. You hold the ruler in your hand again. Its notches are faint but regular, and when you lay it across the galaxy distribution, it fits like a familiar key in a new lock. A yardstick born in a baby universe becomes a measuring tape for dark energy's push today. Spin arrives almost as a courtesy. As proto-galaxies tumble into halos, tidal torques from neighboring structures twist them, lending angular momentum that will later decide whether a city of stars becomes a grand spiral with lanes of dust and neon knots, or a rounder, quieter elliptical with stars on crossing paths. You feel the spin as a slow-turning platter beneath your feet, a gentle centripetal reassurance. Disks settle thin where gas can cool and maintain order. Spheroids puff up where mergers and feedback stir chaos. Yet even in chaos, the web's memory persists. Satellites trace arcs. Streams of stripped stars ribbon the halos. Shells and rings whisper of collisions long digested. The growth of structure is a conversation between gravity's appetite and pressure's scruples. In voids, the expansion runs a hair faster than average, carrying matter away and deepening the emptiness. In clusters, the expansion is resisted, sometimes even locally reversed, as gravity binds thousands of galaxies into a hot X-ray bright city. You stand in a void and hear almost nothing, only a low wind. You stand in a cluster and hear the sibilant roar of plasma at tens of millions of degrees, electrons buzzing past. Protons in a storm of light you cannot see with eyes, but can feel as a photon-thick heat on the skin of your thought. Not every thread is luminous. Some halos never gather enough cool gas to light up. They remain dark, invisible except through their pull on the paths of stars and the smearing of background shapes. Others light briefly and then go quiet, their fuel gone or heated beyond recall. Still others are vandalized by neighbors, tides strip their outskirts, ram pressure removes their gas, harassment and mergers change their orbits and forms. Beneath the variety, a single growth curve persists. Small things first, large things later. Bottom up, hierarchical, a ladder of assembly where today's giants are yesterday's villages stacked together. Springel et al. 2005. Maybe the universe just loves to repeat patterns. Accretion in streams, pauses in reservoirs, outflows in breaths, trees drinking the same river at many bends. You glance again at the web as a whole. Its filaments are not random spaghetti. They align with the eigenvectors of the tidal field, highways channeled by the same mathematics that sculpted them. Galaxies know this. Their spins and shapes can correlate with the filaments that host them, a kind of urban planning by invisible hands. If you could run your fingers along a filament for 100 million light years, you'd feel a faint grain, like wood that has been planed in one direction. Turn at a node, and the grain knots, dense and multi-directional, a place where clusters bloom. Evidence piles in layers. Redshift surveys paint pointillist maps that, at a distance, become threads and walls. Lensing reconstructs projected mass, revealing halos where starlight is thin. The CMB's lensing and peak structure check the same totals from a different epoch. BAO places rulers, galaxy clusters, counted by mass and redshift, place clocks. Simulations tested against all of it show that a cold, collisionless dark matter, plus ordinary gas, stars, and black holes, governed by general relativity, produces a web so close to ours that you feel a small shiver of recognition. Eisenstein et al. 2005. Springel et al. 2005. Still, humility sits in the passenger seat. On the smallest scales, debates flicker. Are inner density slopes as steep as pure dark matter simulations predict, or does feedback soften them? Do we miss faint satellites because they're truly absent, or because we haven't looked with enough tenderness? The broad symphony is in tune. A few chairs squeak. That's fine for a bedtime mind. It means there's work to wake to. You leave the vantage and step into a galaxy that has just found its balance. Its disk is a slow whirl of starlight. Spiral arms lift from density waves like white chalk arcs. The bulge glows amber at the center. The smell in your imagination is warm dust and cold metal, an observatory dome at midnight. You put your palm to the railing of a bridge that crosses an inner ring and feel a vibration, a memory of the drumline we tracked from ripples to peaks to maps to rulers to this, a city of stars that keeps time with a universe that has no conductor and yet holds a tempo. In the quiet that follows, a thought floats up and lingers. How ordinary the recipe is, how extravagant the result. Gravity plus initial ripples, gas that can cool, feedback that breathes no baroque instructions, just patience and thresholds. Maybe the universe just loves to repeat patterns, from breeze to gale, from sand to dune, from ripple to galaxy. You close your eyes and let the web settle around you like a hammock, taut along filaments, soft in voids, cradling a billion suns that will never know your name and yet have always kept your time. You lean on the railing of a quiet universe and feel, at first, nothing unusual, just the gentle ease we've been tracing since the afterglow. Then your fingers notice it. The rail is pulling away a touch faster than yesterday, as if the cosmic balcony itself is retreating while you stand still. Expansion has always carried you outward like a river, but now the river discovers a gradient you didn't expect, a quickening you can sense in your bones. The galaxies at the far shore do not merely drift, they accelerate. It's a hush that becomes a shiver. Something with negative pressure, a softness that pushes, is woven through spacetime's fabric. The clue arrives not as thunder but as candlelight, standard candles, to be precise. Type Ia supernovae, those near-identical detonations of white dwarfs reaching a critical mass, are bright enough to be seen across billions of light years and uniform enough to act as distance markers once you calibrate their light curves. You hold one in your mind's palm, a pearl-white blossom brightening, plateauing, fading, its shape whispering its true luminosity. Compare that known wattage with how dim it appears. Add the redshift, the stretch of its spectrum by expansion, and you can place it on a cosmic map. In the late 1990 seconds, two teams did this with care, and the map did something astonishing. Distant supernovae looked too faint, as if, after a long, slow era, expansion had started to speed up, pushing them farther than a decelerating universe would allow. Res et al. 1000 1998. Perlmutter et al. 1999. You listen to the graphs as if they were music. The Hubble diagram's points don't sit where a matter-only cosmos would place them. They curve toward a story with a repulsive component. The simplest fit is an old idea dressed in crisp data. A cosmological constant, Lel, the same term Einstein once introduced to hold the universe static and later regretted, now reborn as the cleanest description of a fluid with equation of state parameter, W equals 1 pressure, equal in magnitude and opposite in sign to its energy density. In general relativity's ledger, such a fluid doesn't dilute as space grows. Its energy density stays constant per unit volume. Make more space, and you get more of it, like a quiet royalty that pays out proportionally to the acreage you add. The result is acceleration. You feel the surprise as a cool wind at your collarbone. Not faster motion through space, but faster growth of space itself. The sensation of negative pressure is counterintuitive, so you try a tactile analogy. Imagine a rubber sheet with a built-in tension that wants to spread. The more sheet there is, the more it stretches. Dark energy is not a force acting on things within space. It is a property of space-time, a way the geometry responds to a uniform energy density that refuses to fade. You press your palm to the sheet, and it rises to meet you, softly insistent. Galaxies, like beads sewn to the fabric, are carried apart, even as their local neighborhoods remain bound by gravity. Supernovae cracked the door, but other instruments swung it wide. The baryon acoustic oscillation scale the ruler we tucked into our pocket back in Section 8. Serves as a standard length imprinted in the galaxy distribution. Measure its apparent size at different redshifts, and you read off the expansion history, much like reading mile markers on a highway. Layer on the cosmic microwave background's early time snapshot, which pins the initial conditions with startling precision, and a coherent picture emerges. A flat universe with roughly 68% of its energy budget in this dark energy-like component, 27% in dark matter, 5% in ordinary matter. Planck collaboration, 2018. You run your thumb over those numbers. They feel both improbable and inevitable now that you've seen how the peaks, the ruler, and the candles all hum the same chord. The fact beneath the poetry is simple and sharp. The Friedmann equation, dressed with a Lel term, or a fluid with W, is less than 1/3, permits accelerated expansion. Supernovae and BAO and the CMB together say the real universe takes that option. Ries et al. 1998. Perlmutter et al. 1999. Planck collaboration, 2018. You could stop there, satisfied by the parsimony of Lel, but your curiosity paces. Maybe dark energy is dynamical, a field that changes slowly over time, a quintessence with W slightly higher than 1 and evolving, its pressure less perfectly negative, its density not perfectly constant, or perhaps gravity itself changes character on grand scales, mimicking a fluid by altering how curvature relates to energy-modified gravity rather than a new ingredient. You lift these possibilities the way you might lift fabrics at a tailor's. Different weights, different drapes, all meant to hang on the same frame of data. You listen for distinguishing sounds. A true cosmological constant keeps W pinned to swan at all epochs. A quintessence model lets W wander, often toward less negative values in the past. Modified gravity can tweak how structures grow, even if the expansion history looks similar. Observers turn to redshift space distortions, how peculiar velocities squish and stretch galaxy maps to measure the growth rate of clustering, and to weak lensing shear fields to trace the mass distribution's evolution. If dark energy is a smooth, uniform pressure, it should slow the growth of structure, compared to a matter-only model. If gravity has been rewired, the growth might deviate in a scale-dependent way. You sense the test as a stethoscope pressed to the web. Is the heartbeat damped exactly as LCDM predicts, or is there an extra skip? For now, the web keeps time with Lel to a remarkable degree. Though small disagreements, subtle tensions in lensing amplitude, in the Hubble constant inferred from nearby distance, ladders versus the early universe yardsticks, keep the conversation lively. You accept the ambiguity like a mote of dust in a beam. Real, small, a reason to keep watching. Maybe the universe just loves to repeat patterns, a clean theme with a few jazz notes that pull you closer rather than push you away. You try to smell this epoch, absurd as that is. It smells like the inside of a planetarium. Faint plastic, cool metal, a hint of ozone from ionizers. Clean, artificial, slightly uncanny. Dark energy has no scent, no color, no taste. Its reality is statistical, geometric, an inference from how rulers look and clocks tick, and yet the feeling it leaves is sensory. A widening between everything that isn't bound, a gentler curve on distant light's path, a hush that deepens as time goes on. If the matter-dominated era was a drumbeat, the dark energy era is a long-held organ tone, filling the nave so evenly you forget it's there, until someone turns the knob and the room empties. You think of consequences. In a Lel-dominated future, unbound structures recede beyond each other's horizons. The night sky grows static at local scales, but the grand tapestry thins. Galaxies within clusters remain married by gravity. Beyond that, relationships fray. Star formation slows as gas is used and heated. The universe settles into a long afternoon. If dark energy evolves, the afternoon's length and quality change. If W dips below 1-year phantom regime, exotic endings like a big rip enter the conversation, though data today keep that in the realm of speculative lullabies rather than firm forecasts. You let the futures float like dandelion seeds and choose not to chase them. Sleep likes the present tense. A callback comforts you. Once, we thought expansion should decelerate under gravity's pull. Then standard candles whispered otherwise. We checked with rulers etched in the fog and with the baby photos freckles. They agreed. The lesson is not that nature enjoys surprises, though it does, but that multiple, independent witnesses can turn surprise into understanding without raising their voices. That's good bedside science. No drama, just converging lines. Before you move on, you cradle one type ear in your mind again. Its light curve is a shallow bowl of gold, tipped with rose, fading into ash. Embedded in that curve is a galaxy's redshift, a measure of the universe's stretch. Embedded in its absolute brightness is a distance. Embedded in the set of them is a claim about the whole. You think of a village's lanterns seen from a hill. If the path grows steeper beneath you, the lanterns appear farther than you expected for their glow. That's all we did. On a cosmic scale, we stood on a hill of time and read the steepness by lantern light. Ries et Eli 1998, Perlmutter et Eli 1999. You exhale. The railing continues its slow retreat. The floor beneath you, our local group, doesn't budge. It is bound by its own gravity. Farther out, clusters keep their tight grips. Farther still, the fabric's soft insistence wins. In that layered motion is a kind of compassion. What is close stays close. What is far drifts farther, gently, inexorably. Maybe the universe just loves to repeat patterns. Near things knit, far things drift, and the whole breathes in a way that makes room for questions. You are small in this, but not irrelevant. You are a witness with instruments, and tonight that feels like enough. You open a drawer in the observatory of your mind and find two rulers. One is ancient, carved from the fire of the early universe, a length set when the cosmos was still a ringing fluid. The other is handmade and local, whittled from stars whose distances we've learned to measure by patient geometry and rhythm. You place them side by side on the table of the sky and discover, with a small intake of breath, that they do not quite agree. The table is the expansion of space. The disagreement is the Hubble tension. And tonight, you run your fingertips along each ruler's notches until you feel where the difference begins. The first ruler is the sound horizon, the distance a pressure wave can travel in the photon-baryon soup before light lets go. Imagine a drumhead that is also the universe, struck once at the beginning. The ripple races outward until recombination freezes its reach. That frozen reach about a few 100,000 light-years in the old units, but, more usefully, roughly 147 megaparsecs in co-moving measure, becomes a standard length stamped into everything that follows. Planck Collaboration, 2018. You never see the ruler directly. You infer it from the pattern of peaks in the cosmic microwave background, and from the preferred spacing of galaxies, the baryon acoustic oscillation (BAO) feature, like a faint watermark across the late-time map, Alam A. Ali, 2021. You hold this early universe yardstick to the cosmos, and it tells a consistent story. If you adopt the physics we trust for that era, then today's expansion rate, h0, It should be about 67-68 kilometers per second per megaparsec. Planck collaboration, 2018. Elam et al. 2021. The feeling is of cool precision, not dramatic, but steady, like a ruler of steel. The second ruler is a ladder made of light. You begin with geometric anchors, masers orbiting a black hole that sketch circles in radio, parallax from Gaia that measures the tiny wobble of nearby stars, eclipsing binaries in the large Magellanic Cloud that beat like perfect clocks, and you pass that calibration to standard candles. Cepheid variables, whose period luminosity relation lets you read distance from their rhythm. Tip of the red giant branch stars, whose helium flash sets a near uniform peak, and type Ia supernovae, whose light curves can be standardized into reliable beacons. You move outward step by careful step, then stitch the steps together so that distant supernovae write the slope of the Hubble law in the nearby universe. This late-time yardstick whispers a higher number, around 73 kms MPC, with tender error bars earned by years of rechecking systematics. Ries et al. 2022. The sensation is warmer, human wood instead of steel because it's assembled from many small, luminous lives. You lay the rulers across the same table, and the misfit becomes a tactile fact under your hand. It is not a quibble of 1 or 2 kilometers. It is a gap of several, large enough that the two estimates sit 5 standard deviations apart. If you trust their stated uncertainties, Ries et al. 2022. Planck collaboration, 2018. The early universe method, CMB plus standard physics of recombination, leans low. The late universe ladder leans high. BAO straddles the two, but, crucially, BAO by itself measures only relative distances. It needs a calibration. Feed BAO the CMB calibrated sound horizon, and it sides with the lower value. Feed BAO a local calibration from supernovae distances, and it prefers the higher slope. You feel the neutrality of BAO like a spirit level. It won't declare the tilt without a reference. Elam et al. 2021. To learn what each ruler is truly telling you, you trace how they're made. The sound horizon depends on the physics before and during recombination, the densities of matter and radiation, the baryon content, the number of light relativistic species, and the way photons and baryons converse. Change those, even slightly, and the early universe ruler changes length. Shorten it, and holding fixed the angles you observe in the CMB and the positions of the BAO bump, you can coax the inferred H0 upward. Theorists try on models like Taylor's test fabrics. Add an episode of early dark energy that briefly alters expansion before recombination. Tweak the neutrino sector, adjust interactions that change how heat flows in the plasma. Each alteration aims to keep the beautiful CMB fit, while nudging H0 into harmony with the local ladder. Planck collaboration, 2018. You run the cloth over your cheek. Some fabrics itch, some drape strangely, some tear when pulled by other data. BBN yields, damping tails, lensing so the wardrobe remains mostly speculative. The ladder has its own sensibilities. Cepheids shine in crowded, dusty, star-forming regions. Meticulous teams correct for metallicity, crowding, and extinction. They cross-check with independent anchors. The NGC, 4,258 megamaser distance. Milky Way parallaxes, the LMC's geometry, so that no single rung bears too much weight. Ries et al. 2022. Others climb a neighboring ladder using the tip of the red giant branch to tame some Cepheid systematics. Still others calibrate SNE with both. The more ways you climb, the more the view from the top H0 around 73 persists. You can almost hear the workshop where these distances are tuned. Air cool, lamps steady, the soft clack of shutters opening to catch a star's pulse. There are third ways, independent checks that add texture. Strong gravitational lenses, galaxies that split a background quasar into multiple images, also carry a clock in the time delays between those images' flickers. Measure the delays, reconstruct the lens mass carefully, and geometry itself yields H0 without touching supernovae or the CMB. Current samples lean to values consistent with the ladder, though the method's systematics, mass-profile degeneracies, line-of-sight structures require monkish care, for example, H0 Lykow TD Cosmo analyses. Standard sirens, two gravitational waves from merging neutron stars, offer, in principle, a direct luminosity distance from waveform physics. Pair that with a redshift from an electromagnetic counterpart or statistical host population, and you write another point on the Hubble diagram. The few events so far give broad posteriors, but their promise is visceral, a ruler in gravity's voice. You imagine the universe ringing like a bell, and the sound itself bringing you a yardstick. You step back and regard the table as a whole. Early universe, clean, global, elegant, with parameters cross-laced by the CMB's peaks and troughs. Planck collaboration, 2018. Late universe, messy, local, artisanal, with distances built from stars you could almost visit Rias et Alii, 2022. BAO, a bridge between them, geometry's watermark over billions of light-years Alamet Ali, 2021. The misfit is not a failure, it is a frontier. If new physics changed the early ruler's length, the cosmos is more interesting than we thought. If subtle systematics haunt one or more late rungs, our craft can improve. Either way, the conversation is energetic and precise, the best kind. The sensory image that stays with you is simple. Two tape measures unrolled across a wooden bench. One is stamped with frost, the other with candle wax. You press them flat with your palms and feel the mismatch in your skin. You are not upset by the difference. You are curious. Maybe the universe just loves to repeat patterns agreement punctuated by a small, persistent discord that coaxes new music from old instruments. You try a final thought experiment. Suppose you shorten the sound horizon by briefly letting an early dark energy component contribute a few % of the energy density before recombination, then vanish by the time the afterglow is born. The peaks must still land where Planck sees them. The damping tail must still blur just so. The light element abundances must still match the fossil chemistry from section 6. The model breathes, and then, more often than not, wheezes. A few constructions keep time across the data, but many do not. Now suppose you imagine hidden biases in Cepheid crowding or dust. You let them grow large enough to close the gap. Other crosschecks tip of the red giant branch distances. Masers, parallaxes raise their eyebrows. Reality, patient and stern, keeps the rulers closer to their current lengths than your daydreams prefer. It is a kind refusal that feels like a teacher's hand on your shoulder. So you keep both rulers in the drawer and continue to measure. New BAO surveys sharpen the watermark. More precise parallaxes sand the ladder's rungs. Growing samples of lenses and sirens add chords in different keys. Each improvement is a candle carried down a long hallway. The draft is steady. The walls are smooth. Somewhere ahead, either a hidden door will open the physics changing in the early minutes of time, or the floorboards will creak the systematics giving themselves away. Until then, you take comfort in the coherence around the dissonance. Most notes agree. The melody remains. The tension is a harmony waiting to resolve. You look up from the bench and see, through the dome slit, a sky that is quietly expanding. If you could listen as a carpenter listens to wood, you might hear the grain of space-time stretch. It sounds like a long-held vowel, not loud, not urgent. You exhale to match it. The rulers slide back into the drawer, cool and warm to the touch. Tomorrow, you will measure again. Tonight, you admire the patience of a universe that lets you compare its first whispers to its latest breaths, and invites you to notice that they are almost, but not quite, the same. You sit at the shoreline we have circled all night and ask the simplest, slipperiest question. What does before even mean when you stand at the first light? You try to point backward, and your finger finds fog, not darkness fog. Words like earlier and prior are habits of a mind that has always lived downstream. Near the headwaters, time might change texture. The river may widen into a lake where upstream becomes an unhelpful direction. You breathe in that mist and, as your eyes adjust, two paths emerge. One where the edge is rounded so there is no corner to turn, and one where the edge spring-loads you back the way you came. On the rounded path, time does not end with a splintered cliff. It softens. Think of a globe. At the South Pole, south stops being a meaningful instruction. Every step is north. In a similar vein, the no-boundary proposal imagines the earliest universe as a smooth, compact geometry with no sharp beginning. A kind of rounded cap where the distinction between time and space melts, then reappears as the universe cools and expands. Hartle and Hawking, 1983. In the technical telling, you rotate to imaginary time to make the path integral over geometries converge, sum over compact histories without boundary, and then rotate back. In the bedtime telling, you slide your hand over a polished marble dome, feel no edge, and then without a jolt, your fingers find a flat table. Time. The proposal doesn't say the universe came from nothing. It says the earliest region is not a time you could have lived in. Before is like more south than the South Pole grammatical, but without a place to stand. Hartle and Hawking, 1983. Your senses check the story. On the dome, the air is cold and oddly echoless, like a snow cave. There isn't silence so much as the absence of reverberation. That absence is the point. Without a boundary, there is nothing for a wave to bang against and define an initial reflection. The wave function of the universe, the object, the proposal, assigns to whole histories, weights smooth, small geometries more than jagged, large ones, favoring beginnings that are round and simple. It is not a prediction you can see by eye. It is a weighting you might feel as a preference for calm. Later, when time becomes time, quantum jitters unfurl into the ripples we already traced. Inflation takes the baton. Recombination freezes the afterglow. But the very first bars, the rounding, speak in a grammar where earlier is unsayable. On the spring-loaded path, you keep time but refuse the singular break. Instead of a dead end, you meet a trampoline. Loop quantum cosmology, LQC, replaces the classical singularity with a bounce, born from a granular geometry where areas and volumes come in discrete quanta. At Planckian densities, the effective equations pick up a repulsive term, and contraction hands off to expansion without letting curvature or density blow up. Ashtekar, Pawlowski, and Singh, 2006. The sensation changes. The fog becomes air that pushes back softly, like the feeling you get at the bottom of a dive just before buoyancy returns you to the surface. Before, in this picture, is readable. There were earlier times, a contracting phase, whose memory can survive the bounce in subtle correlations. Though the details depend on which matter, fields, and symmetries you bring to the party. Ashtekar, Pawlowski, and Singh, 2006. You put your palm to the imagined trampoline. It is cool and tense. You bounce once, twice. The arc is symmetric only in outline. In reality, dissipation and particle production at the bounce can smear the mirror. So the prehistory is not a perfect negative of the post-history. Yet the crucial relief holds. No unstoppable fall into a singularity. If the no-boundary dome turns before into a category mistake, the loop bounce turns before into a chapter you might someday annotate with data. A low feature in the microwave power spectrum, a particular phase in primordial perturbations, a soft cutoff at the largest scales. Whether those hints are there or not is a live conversation between models and sky. What you keep tonight is the tactile sense that geometry can stiffen and refuse the cliff. Ashtekar, Pawlowski, and Singh, 2006. You widen your listening. Other composers have scored preludes. Eternal inflation that keeps blowing bubble universes while our patch reheats. Ekpyrotic cycles where slow, smoothing contraction preps a rebound. Time-symmetric visions where two arrows of time flow away from a low-entropy waste. We nodded at some earlier. The details differ. Fields collide on higher dimensional bronze. Equations swap curvature terms. Entropy puzzles shift seats. But the shared intuition is that the Big Bang might be a transition, not an absolute start. You taste this thought and it is mint cool and a little sharp, refreshing, slightly unbelievable until you get used to it. Then you do something quieter. You take a pencil and circle the word before. The circle itself becomes the insight. Before is a temporal relation. The earliest universe may not grant that relation the solidity it has later. In canonical quantum cosmology, the Wheeler-DeWitt equation treats the wave function of the universe as, in a sense, timeless. What we call time can emerge from correlations between subsystems, one degree of freedom serving as a clock for another. In a lullaby translation, you lay two metronomes on a table. Neither knows absolute time, but each can keep time for the other. Near the beginning, clocks are scarce and noisy. Only later do many-handed stable clocks, atoms, pulsars, supernovae arrive to enforce a shared beat. Before then, maybe a late luxury. You ask whether these prefaces can be weighed by the sky. The no-boundary proposal makes probabilistic statements about which inflationary histories are favored. In some implementations, it leans toward enough inflation to smooth the world. In others, it tussles with measures that overproduce rarity. LQC promises, in certain versions, a tiny running of the primordial spectrum at the largest scales, a place where cosmic variance is cruel, but not paralyzing. A cyclical ekpyrotic past might imprint distinctive non-Gaussianities, or a blue-tilted gravitational wave spectrum, rather than the red tilt inflation prefers. Each of these is a texture you could, in principle, feel with instruments that have already impressed you. Microwave telescopes, galaxy surveys, pulsar timing arrays. You turn the texture under your thumb, and, for now, it feels like fine grain just beyond tactile resolution. Patience. A sensory image steadies you. You walk along a sandy shore at night. The tide is low, the sand underfoot is cool, packed. Ahead, the beach curves into a gentle point you cannot see around it. You can draw two different maps that agree with your steps so far. In one, the shore ends in a rounded spit that turns imperceptibly into water, and then into a new direction of walking, the no-boundary dome. In the other, the shore continues around the point to a mirrored beach you could have walked earlier, leading down toward a place where the sand grows firmer, and then, just at the limit, springs you back. The loop bounce. The wind tastes of salt and iron. The waves are small. The stars are steady. Either way, your footprints look the same where you are. Only with more steps or a drone's view might the maps diverge. You hear a philosophical rhythm tapping under the physics. We ask for a cause behind every effect. What came before? Behind every now. Science answers by shrinking the class of things that need no further story. Laws and boundary conditions on one side, specific happenings on the other. These proposals move a few items between the baskets. The no-boundary proposal tries to make boundary conditions feel less like special pleadings and more like geometry's gentle fact. The loop bounce tries to swap an unphysical singularity for a regular, law-governed turn. Neither erases or ends questions. Both refine the kind of question that still makes sense. Maybe the universe just loves to repeat patterns. When a word stops helping, you trade it for a better one. When a cliff appears, you look for the path that goes around. You exhale and let the fog thicken and thin. Your heartbeat sets a local arrow. Your warm breath rises. Entropy increases in your small corner, but that is the next section's music. For now, let before be a soft word, not a trap. The practical comfort is this. The parts of the story you can test the ripples, the peaks, the yields of light elements. The web do not rely on whether the beginning is a dome, a bounce, or a cliff hidden by quantum light. You can hold humility and confidence in the same palm. The shoreline is still here under your feet. The tide still breathes. And the sky, patient, patterned, precise, still answers when you ask with instruments and quiet wonder. You rub your thumb along the grain of time and feel it run one way, like fur that lies smooth in only one direction. Stir cream into coffee, and the swirl spreads. Drop a glass, and shards fly. Breathe out, and warmth dissipates into the room. You never see the reverse by accident. That feeling of a preferred direction from tidy to tangled is the arrow of time you live inside, and its shaft is entropy. The second law is the quiet rule. In an isolated system, entropy not only tends to increase, it's staggeringly likely to increase, because there are countless more messy micro-arrangements than prim, special ones. You can hear the law as a soft rustle, cards shuffling toward disorder, sand smoothing underfoot, smoke threading outward. Yet the cosmos complicates the lullaby, for gravity loves clumping, and clumping can look like order and yet be high entropy. You hold both ideas, as if they were stones of different temperature in the same hand. To make sense of the arrow, you turn to beginnings. Most arrows you meet in physics are time-symmetric at the fundamental level. Newton's laws, Maxwell's equations, even quantum unitary evolution run cleanly forward or backward if you flip velocities or complex conjugate states. The irreversibility you feel is statistical, born from overwhelmingly biased boundary conditions. In ordinary life, we prepare low-entropy states, clean rooms, charged batteries, and let them relax. For the universe, who did the preparing? The standard answer is not a who, but a fact. The early universe began in an extraordinarily low entropy macrostate, far lower than a generic hot plasma could have enjoyed. That assumption has a name with the honesty of a label maker. The past hypothesis, Carroll, 2010. You pass your palm over it. It feels smooth and austere. Gravity's role is the deeper texture. For a box of gas with no gravity, maximum entropy is uniform spread. For a self-gravitating medium like the cosmos, the opposite happens. Uniformity is special, not generic. Left to itself under gravity, matter prefers to make clumps, then denser clumps, then stars, black holes, and, ultimately, if nothing stops it, vast collapsed objects. Those states contain tremendous gravitational entropy. Roger Penrose framed this point with a geometric elegance. Early spacetime had extremely low Weyl curvature, the piece of curvature that measures tidal distortions and gravitational degrees of freedom, suggesting the initial condition minimized gravitational entropy even as the thermal plasma was. Near local equilibrium, Penrose, 1979. In your hand, the distinction feels like two fabrics layered. One, thermal, already rumpled to comfort. The other, gravitational, ironed preternaturally flat. As expansion proceeds, the gravitational sheet wrinkles on purpose, and entropy climbs as structure forms. You test the sensation in small parables. A cloud of gas in deep space cools as it expands, but because of gravity, it also fragments and collapses locally, converting potential energy into heat and light, and increasing total entropy. Galaxies and clusters, rife with hot X-ray gas and studded with black holes, are not orderly in the thermodynamic sense. They are entropically luxuriant outcomes of a low-gravity entropy beginning. Black holes, in fact, dominate the cosmic entropy ledger. By far, their horizon areas translate to entropy so huge that all the photons and neutrinos of the universe are a rounding error beside them. You picture a ledger where one entry, written in thick ink, dwarfs all the others. The page smells of singed paper and iron. Still, your inborn objection taps. If the microscopic equations don't care about time's direction, why doesn't entropy sometimes flow backward? In principle, with exquisite correlation setting, you could turn shattered glass into glass again, cream unswirled, galaxies unformed. But the phase space volume for such conspiracies is unimaginably tiny. Boltzmann gave the argument its backbone. Macrostates correspond to wild numbers of microstates. Systems move, with overwhelming probability, from less numerous to more numerous sets. Loschmidt's paradox, then why not the reverse, is answered by the past hypothesis. We began in the special corner, and dynamics did the rest. Carroll, 2010. You hear the resolution as a door latch clicking softly. The cosmic narrative fits your fingertips. Right after recombination, the universe looks smooth in matter density, low gravitational entropy, yet locally thermal in radiation-high non-gravitational entropy. As time flows, small density contrasts grow. Stars ignite, heavy elements brew, black holes swell, radiation redshifts, the overall entropy climbs. The arrow aligns with the expansion not by logical necessity, but because of that low entropy start. Had the initial gravitational field been a chaotic froth, the arrow might have been absent or tangled. Instead, the early smoothness so beautifully captured by the evenness of the microwave sky quietly purchased your sense that breathing in yesterday and breathing out today make different meanings in your chest. Penrose, 1979. Carroll, 2010. You run your finger along a speculative seam. Did inflation set the arrow? Inflation makes the universe smooth, yes. But the second law demands that if inflation started, the conditions for inflation were themselves special. A patch dominated by a nearly uniform inflaton field with low gradients is not generic on the space of all possible initial data. Inflation then amplifies that specialness, stretching a low entropy seed into a vast domain where ordinary thermodynamic arrows can blossom. So inflation may explain much of the arrow you feel, but it borrows low entropy to begin. The past boundary condition remains the ultimate mystery or axiom, depending on your taste. Carroll, 2010. The thought tastes like peppermint. Cool, clean, with a hidden bite. Penrose proposes a sharpened intuition. The Weyl curvature was essentially zero at the bang, and grows thereafter the Weyl curvature hypothesis. In tactile terms, spacetime's tidal grain was polished smooth at the start. Singularities at the other temporal end inside black holes are the opposite. Huge Weyl curvature, maximal gravitational disorder. The beginning and the interior of a dying star are both extreme, but they are extremes of different kinds. You feel the contrast as two stones, one river smoothed, one jagged held in either hand. Penrose, 1979. The poetry sits lightly over a hard claim. The arrow is geometrized. Let the narrative pass through your senses like air. You are in a kitchen after midnight. The fridge hums. A glass of water warms to room temperature. Nothing ever spontaneously chills. On the counter, flour dust settles. It never leaps into a bag. Outside, galaxies drift into deeper isolation as dark energy relaxes the web. Within clusters, black holes slowly dine. The universe and your kitchen share a grammar because both inherited a bias. Low entropy in the past. Maybe the universe just loves to repeat patterns, simple initial harmonies that allow rich, irreversible melodies without a conductor. A skeptic in you wonders about rare fluctuations. If you wait long enough in an equilibrium universe, couldn't observers like you pop out of chaos? A Boltzmann brain winking briefly into awareness, then gone? That grotesque possibility is precisely the cautionary tale. A cosmos where typical observers of fluctuations is epistemically unstable and observationally unlike ours, which bears a coherent, long arrow with fossils in every drawer. Our sky's deep consistency, CMB to nucleosynthesis to structure, argues powerfully that we are not such flukes. The arrow is not a local quirk, it is a continent-wide wind. Carroll, 2010. You feel relief like cool water on the neck. You revisit the beginning with gentler eyes. Whether the start was a rounded dome with vanishing Weyl curvature or a quantum bounce that preserved calm gravitational initial data, the crucial feature is the same: specialness. The early state was atypical in the measure theory sense, not by decree but by count. That specialness is not an embarrassment. It is a datum, as worthy of respect as the value of the electron's charge. Perhaps a future theory will derive it from deeper symmetries or selection effects. Perhaps it is an axiom we learn to accept the way we accept that triangles' angles sum to 180 degrees on a flat sheet. You breathe in, your ribs lift, heat leaves your skin, entropy rises gently around you. The arrow, tonight, is a lullaby rather than an edict. A last image. You stand in a long corridor lit by candles placed every few meters. Behind you, the wax is tall and smooth. Ahead, each candle is a little shorter, the floor a touch more mottled with drips. You walk forward. The air smells like warm paraffin and dust. You could, in principle, balance all the drips back upward, sand the floor, re-pour the wax, but the improbability is oceanic. So you keep walking, and the corridor keeps making sense. The universe is still here, quietly turning low note into higher chorus, smooth beginning into textured now. Maybe that's all the meaning you need before sleep. The arrow points from simplicity to story, and you are a sentence written along its line. You lie on the observatory floor and let the dome slit frame a thin triangle of night, the kind of view that makes you feel both sheltered and infinite. You breathe, and the air smells faintly of dust and cold metal. Somewhere, a relay clicks. You think about how much of this story is already inside you: helium from the first minutes in your lungs, oxygen cooked later in stars in your blood, iron from ancient supernovae in the hem of your thoughts. You wonder what it means to occupy a universe whose first moment you can neither visit nor ignore, and you decide to answer softly. It means you are a late paragraph in a very old book, but the ink that writes you was mixed at the beginning. Facts steady you like handrails. The cosmos today is about 13.8 billion years old. The light filling your instruments from every direction is a 2.7 Kelvin whisper of its hot youth. The energy inventory is mostly dark, roughly 68% in dark energy, 27% in dark matter, and about 5% in the baryonic stuff you can touch and taste. Planck Collaboration, 2018. Those numbers are not slogans but measurements, drawn independently from the afterglow's acoustic peaks, from the galaxy map's fossil ripples, and from the lanterns of supernovae. You carry them like smooth stones in your pocket, proofs against drifting into pretty confusion. Then you let the handrails go and feel. A human life is a brief spark in a long twilight, yet your brain, the size of a small cauliflower, humming at about 20 watts, holds a model of an expanding space-time stitched from equations and sky. That is not arrogance. It is correspondence. The freckles in the microwave sky line up with the notes of inflation we inferred. The yield of helium matches the minutes-old forge we simulated. The web of galaxies repeats the pattern gravity promised. Nearby standard candles curve the Hubble diagram toward a late-time push. You rest your ear to the universe, and the rhythm you hear is one your instruments already learned to count. You taste humility in the scale of what remains unknown. Dark matter's nature, the particle or band of possibilities that holds your galaxy together, still refuses to introduce itself. Dark energy's pressure hums without telling you its origin. The beginning's boundary rounded, spring-loaded, or something stranger still wavers like heat over a road. But that list is not a lament. It is a curriculum. Each unknown has handles where minds can hold on. Maybe the universe just loves to repeat patterns. Clarity followed by a new kind of question. Answers that make room for better ignorance. A factual thought returns with a quiet tap. Most of the observable universe is not observable to you personally, not just because of distance, but because horizons exist. There is a limit to what any one world line can see. Light beyond a certain co-moving radius will never reach you if acceleration continues. The far becomes forever. That horizon is not a cruelty. It is a geometry. You close your eyes and picture a shoreline at dusk, the water murmuring beyond a sandbar you will never wade past, and it comforts you to know the ocean still works in the dark. You try on a gentler purpose. If you are a late paragraph, perhaps your job is annotation, not to revise the first chapter, but to understand its cadence, to leave footnotes of care for those who read after. Peebles likes to remind us that cosmology grew from a tangle of rough ideas into a precision science, only because instruments and patience learn to talk. Peebles 2020. You think of the horn antennas, the bolometers, the radiometers, the spectrographs, of glass polished until the cosmos could see itself in it, of software taught to be as quiet as space. Meaning, here is a practice. Carefully match premise to measure, refuse shortcuts, enjoy when the data scold you into a better theory. Then you look inward, and the scale flips. Entropy's arrow you felt a moment ago is the same in your kitchen and in your sky. Your mind's ability to remember yesterday but not tomorrow is a local version of a global bias that began in a low-entropy past. The way your stories grow from simplicity to texture echoes the way structure grew from ripples to filaments. You are not the center, but you are not foreign either. The rules that made the first minute's helium made the neurons that now consider it. That continuity is a kind of tenderness. A small factual image blooms. Somewhere, right now, a photon that last scattered 7 billion years ago is finishing its long, straight line by tapping a detector on a satellite. Its energy is tiny, a whisper of a whisper, yet your species knows what to do with it. Average it with billions of others. Subtract foregrounds, fit a spectrum, read parameters. The act is mundane and holy at once. It is very human to turn a noise into a number and a number into a story, and to check the story hard enough that it can survive the next midnight. You try to name what the Big Bang means and decide not to. It is not a firecracker, not a divine punctuation, not a single dot of everything. It is a limit where your best laws ask for new company, an early interval where expansion and heat and quantum noise together set the table for everything else. If the beginning is a dome without edges, a bounce, or a cliff you cannot crest, your place is downstream either way. You are the part of the universe that woke up enough to notice it has a history. The room is quiet now. The slit shows a triangle of night that seems wider than before, as if acknowledging the work you just did. You put your hand flat on the floor and feel the faintest vibration air system, building sway, your own pulse. You think, I am the improbable way the first moment meets small hands and careful tools. Maybe the universe just loves to repeat patterns, from boiling plasma to quiet oceans, from random jitters to nightly breath, from the first instant to this one, and in each place, a chance to practice wonder with accuracy. Let the pace soften, like a tide that has turned and now slides back down the sand, lengthening its reach with each slow breath. You are lying beneath a sky that no longer needs you to count it. It keeps its own time. The first instant, whatever its true geometry, has done its work. Inflation's gust is memory. The plasma's music is fossil. The light elements are asleep in stars and in you. The afterglow hums low, a lullaby just above silence. The universe is still here, quietly working while you sleep. Galaxies drift a little farther. Clusters breathe heat into their halos. Dark matter holds its shape like a careful hand under porcelain. Dark energy presses with a softness that never quite relents. Somewhere, a supernova is taking a deep breath for tomorrow. Somewhere a planet cools enough to dream of oceans. Let the explanations fade into images. A ruler etched in the fog. A ripple ironed flat, then saved as freckles. A web stretched between towns of starlight. Candles on a long corridor. Wax softening forward. A beach where the word before grows gentle and becomes a curve instead of a cliff. These are not puzzles now. They are weather in your mind, clouds you can watch without needing to name each one. You carry only what rests well in your hands. That beginnings leave patterns. That patterns welcome questions. That questions can be kind. Breathe in once more. Feel the body's small gravity, your ribs rising like little horizons. Breathe out and let the room recede into its own slow expansion. You are safe in this moment, bracketed by laws that run faithfully and by mysteries that do not hurry. The night will hold, the background will sing, the past is simple, the future is generous, and you are the quiet middle, turning wonder into rest,